Hi everyone, welcome to the Discord EPC workshop on building performance assessment towards next generation EPCs. My name is Panayota Hadjipanayotidou, working for CERT, the Center of Research and Technology Hellas, who is the project coordinator. I'm a member of the project management team. Let me start this workshop with some brief information on the project and its vision. So, Discord EPC, titled Next Generation Dynamic Digital EPCs for Enhanced Quality and User Awareness, aspires as a project to deliver the next generation of dynamic performance certificates for the operational and regular assessment of buildings' energy performance. It relies upon and adjusts accordingly to the smart readiness level of the buildings and the corresponding data collection infrastructure and management systems, and builds upon actual data and the digital twin concept to calculate energy, environmental, financial, and we also have human comfort indicators, and through them deliver the EPC classification of the building and reports on additional information. The project is built on BIM literacy, integrating smart meters, actual performance-related data, and activities profiling into the building's digital twin. We aim to provide sufficient background for the delivery of recommendations for the required upgrade of existing standards to enable the integration of the dynamic EPC concept. And we also introduce some aspects on geolocation and polluter-based practices into the EPC rationale. We anticipate to foster this way the energy-saving consciousness of building users and provide regular information on the actual energy performance of the buildings and suitable incentivization for improvements and upgrades. The project will end up in a user-friendly, reliable, and cost-effective informative tool for the end user, both the wide public and professional, as well as in our vision is to establish the grounds for turning EPCs registries into consistent policy feeding mechanism. We are in the middle, halfway there in our project duration. Today, the aim of this workshop is to present some initial findings on of the project, and we also have the pleasure to host presentations from other institutions and sister projects as well. And we can all discuss further the subject of buildings assessment. The workshop is structured under 4 sessions. Integrating the different aspects of building performance assessment, that is smart buildings and energy efficiency, integrated human comfort into energy certification, advancements in building sustainability assessment, and the last session is monetizing buildings energy performance, the use of life cycle costing indicators. We'll be accepting questions at the end of each session, so all attendees are welcome to write in the chat any questions and initiate this way discussion with the presenters. That's all from my side. Thank you for participating. I give the floor to Meja Susnik to introduce the presenters and proceed with the sessions. Thank you.
Thank you, Panayota. Okay, so we can start with the session 1, so smart buildings and energy efficiency. And our first presenter is Giacomo Chiesa from Politecnico di Torino, and he is participating in E-DICE project. So Giacomo, the floor is yours.
Okay, thank you to everyone. Very happy to be there, and thank you very much for this kind invitation of our sister project. My presentation of today will focus on some of the first results that we get by our E-DICE project. In particular, we will focus on an automatic dynamic energy simulation platform that uses Energy Plus as basic, and that we are developing at Politecnico Torino under multiple project support. Before starting, some few words on the sister project EDICE, Energy Flexible Dynamic Building Certifications. Some of the aspects that we will face in the project support the fact that we will test the usages of dynamic simulation to reflect the dynamic behavior of buildings that currently in current leveling system are in several cases not able to accurately reflect, for example, performance gap phenomenon that has been detected between certification and operational elements. In addition to that, we support the fact that steady-state approach is not able in all of the climate, at least, to reflect free-running technologies functionality, especially during the cooling season. And so we aim to support and reflect building dynamics for maximize it, and it will include in labeling approaches of free-running buildings, so when systems are off or not installed like in traditional Mediterranean buildings. Focusing on the presentation of today, I will introduce a new dynamic simulation platform that we consider at present to use Energy Plus in the line of simulation engines. Nevertheless, the approach may be further replicated using different type of platform based on other engines. What the platform do is the possibility to automatically manage the input file, support extra functionalities, manage massive simulation automatically, and compare monitored and simulated data in server-to-server communications. As shown in small schemes, this is part of a large part of the project in which we also include a project middleware developed by the MTech partner on the FUSI platforms that includes the dynamic engine performance certification protocol supported by our web package 2, and that store geometries, physical, technological data from buildings, plus weather informations and monitoring data in itself. The dynamic simulation platform, on which we present an example, is able to automatically manage simulation input and change them, to run simulation in multiple core and parallelize them, and to calculate customized key performance indicator on both simulated and monitored data itself. The tool is a Python library. It's developed under multi-actions. The DICE action is the one funded by the DICE project. There is another in parallel that support forecasting and climate advanced analysis. The tool is called PREDICE, so Python Real-Time Energy Dynamics Climate Evaluation. And for the DICE development action support automatic simulation and simulation user scenario pre-built for making very simple to end user to use the aspect. You don't need to know and IDF, which is the input file energy plus structure, or to know Python coding or other type of coding languages. It includes automatic change in simulation input output of data and support parametric sensitivity analysis. It also compare with another scenario of usages, monitor and simulated data to detect performance gap in semi-real time. It supports also free-running devoted key performance indicator and simulation changes. Plus, it's based to be used locally or in server-to-server, and also allow REST communication for manual or automatic runs. Some of the first input may be found in this journal. And also thanks for sure all my research staff, so also engineering person, engineering grass, so that you would strongly participate and develop the tools. The tools architecture is based on these three models. So on input editor models that are clearly not visible by the end user, that includes pre-built actions that allow, for example, to change insulation level, add insulation, roof walls, change window types, add shading system, fixed and movable, change control actions or control thresholds for system in the models, add scheduled ventilation, modify ventilation inputs, activate, deactivate, or add system in simple HVAC in this case, change occupancy and other type of profiles. The model in itself may have single values or multiple values to support the elements, and pass the data to the runner mode. The runner mode is able in the specific case to support and parallelize the simulation if we are, for example, running sensitivity analysis or multi-comparison analysis using the number of calls of the system in itself that is able to work on single PC or large server facilities. The third model of the library is an output and KPI calculator model that support all type of basic output of Energy Plus, but a specific and a long list of specific developed key performance indicator in the project in itself, from primary energy to appliance CP factors for natural regulation, for example, support predictive mean vote, predictive percentage of dissatisfied calculations, adaptive thermal comfort according to the last European standards, analyzing indoor air quality, EQI index, and so on, in line with potential, and may also be in some way personalized under request. That's KPIs may be supported in parallel to simulation and other type of inputs like forecasted data, measured data, black box model analysis, and so on. We also calculate the fictitious cooling, which is a new indicator that translates free-running discomfort into a sort of fictitious energy use. The tool in itself also includes an EPV compiler model, is able to support automatically the calculation using actual meteorological monitored data from weather station connected in cloud, weather IP services, or weather forecasting. Other development action, this also include a large translation for XCDF4 databases. An example of a basic user scenario is this one. On the left, we see specifically the input required by the user. So an IDF file built up its to design builder whenever is the user CAD interfaces. Energy Plus weather files for this scenario, which is the sensitivity one, or a CSV for other scenario like performance gap or monitored data from the metro stations if needed. That may be retrieved by the server with the middleware communication. And in addition to that, we have a precise input file, which is a JSON at present that's very simple to be compiled. In future, we'll have a graphical user interface with available actions in which we put required key performance indicator and variation in the inputs needed. The results are on the right. First of all, a CSV file with all of the simulation required. For example, if you make sensitivity analysis with 1,000 simulation, its simulation at the end will retrieve in one row, in one line in the specific data frame, which the type of input and results in aggregated key performance indicator, plus a folder for each simulation, which the time step results, so early sub-early results of the required key performance indicator, plus graphical representation if at the beginning, like as 1D, 2D energy signature, couple plots of different variables, adaptive thermal comfort plots, or other type of representation like this one with a series of time series. Current scenario of use, so pre-built scenario with very simple interface for site ADF input, weather input, and etc. For the DICE development action, so under the DICE project, are the sensitivity analysis that perform parametric analysis and sensitivity analysis by modifying massively the input files. Performance gap detections, which is a scenario that may be run each 24 hours, each week, for example, on our demo case and the test by the project middleware. They return the gap between calibrated models and the monitored data and the actual meteorological here. In this case, we adopt the fact that the model works 2 times automatically, one under standard 6798, for example, one for occupancy, and the second one under an inspection, after inspection plan modified models based on the protocol developed in the project. On the point of view that may support actions on reducing the performance gap by informing end user and technical user. In addition to that, we have a model verification semi-automatic scenario that support the calibration process to minimize root mean square error and mean bias error in between consumption or temperature for simulated and monitored data. Example of simple runs of the tools, maybe here retrieved. That's an example of what we can get by the first type of scenario, so sensitivity analysis, simple, typical residential flat with the runs. In this case is with mechanical system on, changes are insulation wall and roof, independently, change window tiles, window to ratio modifications, and that's an example of potential retrieval input comparing worst and best condition in the 1,500 simulations for a predicted percentage dissatisfied. And on the right, we have an example of the impact in between each of these specific variation on the net energy mix of an indicator and the request. A second potential sample results of the sensitivity analysis. This is based on one of the real demo case building that we have in our DICE project. In this case, it's a simulating an outdoor climate, and the real one, which is Alpine, northwest of Italy. So we simulated for road. This is a free-running building, which we change and modify air exchange for hours of ventilated cooling, shading control threshold, temperature, and global horizontal radiation, and overrun length if needed to be added, like potential retrofitting. And that's some example for the worst to the best conditions in terms of relative thermal comfort, and all this variation in the specific input variables act on the number of hours on the different category of adaptive thermal comfort. That is interesting support, for example, starting design actions on to suggest the modification at the end of the certification protocols. Another sample of application scenario, in this case, is the verification scenario. Semi-automatic. This is a case of a real demo building in DICE, that's a school buildings. And we immediately see that on the left, we have the basic results, monitoring and simulate the standard of the school. Since we are in post-COVID condition, the school ventilation was drastically increased. That's a random ventilation because the windows are open manually. And we found and work with this calibration scenario, verification scenario, and at the end, we reduce calibration signal to very acceptable results, and also the behavior was retrieved in the modeling itself. And what's very interesting is that clearly this model was based in 2021 data, and for 2022, the calibrated model is still valid. Next step and limitation on the supporting tools that we are developing is clearly larger application and long-run test with automatic runs by our project made to work on DICE demo cases in the different countries, support dynamic energy performance certification test inside the project. We're testing it on the ANEA Living Lab in Rome, which is our national energy agency for Italy, with very good results at present. The model may support very advanced changes in free-running control of the buildings. One of the limitations that mainly work in Energy Plus version 8.9 or 8.x will potentially translate to 9.x in future projects. That's not done. It's possible to be done. The input managing file is in a JSON format. We can translate it in future in a graphical user interface, supporting very easy usages of the tool. We are working on other developing action to include optimization algorithm and to reduce the time to produce simulations. Since Energy Plus is a fixed time to producing a very complex model, to pass for some usages to white box model to surrogate modeling. I think that's the basic elements of this advance in sample applications of dynamic energy simulations, including the fact that we may manage input, control outputs, and support automatic comparison between monitored and simulated data to support some specific strategies. Clearly, this is based on Energy Plus. In future, maybe based on totally different type of tools of engines, because it's mainly the process in itself that is also tested in the project. So I thank you very much. I leave the floor back.
Thank you very much, Giacomo. This is really interesting presentation. As mentioned before, if you have questions, please write them in the chat, and at the end of the session, we will discuss all the questions at once for the whole session. So thanks again, Giacomo, and we can move to the next presenter. So that is Carlos Ochoa from Ministore project. You can share your screen and begin with your presentation.
Good morning, everybody. My name is Carlos Ochoa. I work at the International Energy Research Center, IRC for short. We are based in Tyndall National Institute, which is the largest research center in Ireland. And I want to thank the D2 EPC project for inviting us. The title of my presentation is High Capacity Thermal Storage Solution for Residential Buildings. This type of system will increase the energy efficiency. This system has been developed in the context of a Horizon 2020 project, which required residential thermal storage with high capacity. The project is named Ministore. It is led by the IRC with participation of partners from the EU and Switzerland and includes the SGS. The main objective of the system, as mentioned, is to develop a compact residential thermal storage system based on thermochemical material. Other aims that were asked by the call and had to be met is that the storage capacity has to be more than 10 times than the storage capacity of water. It's using photovoltaic thermal panels to power this process. The thermal storage material is 0.72 cubic meters, which was a requirement that has to be less than 1 cubic meter. The payback period is 6.7 years, according to the calculations, and we have been estimating that it reduces energy by 44% in a typical household. It also combines thermal and electrical energy using a home energy management system. We are using thermochemical materials, which are the next generation of thermal storage materials, and they use chemical energy. They are contained in a sealed vessel that is used for daily and multi-day energy storage. We're also using phase change materials that store energy as latent heat, and they supplement heating, cooling, and storage. And the energy storage density is over 180 kilowatt hours per cubic meter, and provides the necessary inputs through photovoltaic panels that produce both heat and electricity. In order to illustrate the concept, you can see it here. You can see on the right that the input is the solar energy that goes from the panels for heat and power, and they can produce both heat through heated water to the thermochemical material, which is then distributed to heating and cooling components that are then set to the heating and cooling systems of the household. The PVT panel also produces electricity, which charges a battery, which can then be used for energy trading or to share with the household. All this concept is managed by the home energy management system that responds to what the user wants and also to what the prices in the grid are in order to sell the electricity. All this is done without hurting the occupant's comfort. As mentioned, the TCM reactor uses ammoniated calcium chloride salts, and uses a reversible reaction. And for those that know about the chemistry, here are the reactions. The system, because in order not to corrode, uses ammonia gas, which includes a typical refrigeration cycle, which has a compressor, condenser, etc. There is a heat pump to upgrade the heat released by the ammonia condensation. And there are phase change materials that contain in vessels that store the heating and cooling. Also, there is the solar field and the building energy system that provides necessary heat and input for electricity. In order to see the reactions, this is what has been mentioned before, that the electricity is collected by the photovoltaic thermal panel and is either sent to a battery for storage or for solar heat. Then the ammoniated salts have a reaction from gaseous ammonia, which is then passed to a condenser or through pressure made liquid again. And then the condensation that is produces heat is then sent to a heat pump, that is then upgraded the heat in order to have more power, either to the hot exchange material or for the housing itself. Then the same is produced at night, that the ammonia is evaporated, which then is passed to the condensator, to the thermodynamical reactor, and then again the same cycle. So this produces a reaction that is cycling and is practically endless. So it's also sustainable. And this is the same for the summer nights, that it passes from the ammonia tank, is then evaporated, and then pass again to the salts, and again to the system that connects to the household. The project will be demonstrated in 4 demonstration sites and 1 pre-demonstration site. The pre-demonstration site is in Thessaloniki. Actually, it's in the premises of CERT, ITI. Then there is also another site on the Demokritos University of Thrace in Greece, also in a private house in Sopron, Hungary. Another one in the managed by the municipality of Cork in Ireland. And the last one that is in the dormitory apartment in the University of Santiago de Compostela in Spain. So these demo sites have been selected because they represent different climatic conditions, as well as different socioeconomic features. Of course, we can ask ourselves why there isn't so much energy thermal storage in our houses right now, and why we have to pay a lot for heating energy in the winter when we can get it from the sun. These have been the main aspects that have been identified as obstacles: the technology, the price, the regulation, and the consumer acceptance. For example, the technology, we still need to exploit the technology and know more in order to make it safe and reliable. This means that we can collect enough heat that will be useful for the homes. Then price is another factor, because thermal storage has to compete, for example, with water heaters, which are well known and are in our houses everywhere. But in comparison, the technology of thermochemical and phase change materials can be between 5 to 10 times more expensive. Then also we have to deal with regulation, since regulation has been made for the traditional technologies, so they do not always acknowledge the newest advances. So this is also an effort for standardization. And of course, last but not least, is consumer acceptance, because if the consumer is not confident about using these systems, it will never take off. So all these elements are being explored in the project, and we hope to provide you with updates very soon on all these elements. So this concludes my presentation. So thank you. If you have any questions, as Mija said, you can write them down.
Thank you very much, Carlos, for your presentation. Yes, as mentioned, questions in the chat. Okay, so we can continue with our 3rd presentation within the session 1. This is Cristiana Pantelli. She is one of our partners in the D2EPC project. Cristiana, you're here?
Yes, thank you, Mia.
Okay.
Just need to share the... Can you see my screen?
Yes.
Yeah, thank you for the introduction. As Mia said, I'm Cristiana Pantelli from presenting Cleopa, GmbH, and part of the D2EPC project. I'm going to present you the last presentation of this first session concerning the smart readiness indicators analysis for EPCs. Just a brief overview of smart readiness indicator in case anybody in the audience is not familiar, highly unlikely, but just in case. So a smart readiness indicator was introduced in 2018 from the European Commission as a part of the recast directive on the energy performance of the buildings. SRI is actually a measure of the intelligence of the building systems as an asset-based rating system for measuring the smartness, and it's expected to promote the adoption of smart building technologies in the building sector in order to contribute to a higher energy performance and subsequently reduce the energy consumption of the buildings. These indicators, the SRI indicators, are relatively new and developed in the beginning of the last decade within the European standards. And this is also in line with the fact that the developments in the market are currently on smart building technologies have a rapid increase in the last couple of years. Here we can see the domains and the categories of smart readiness indicators. We have 9 different domains, which include actually the mechanical systems of the buildings, as well as the electric vehicle charging and monitoring and control. And there's also 7 impact categories that each one of these domains have on these impact categories. Here's an example. On the left-hand side, we have the domains, the mechanical systems, and on the top row there's the impact categories. So this the impact of each of the domains is expressed as a percentage, and we'll also have an overall aggregated score, the SRI score, which is also presented in the SRI assessment. So D2EPC, how we integrated the analysis of smart readiness indicator in D2EPC project. We aimed, in one of our tasks, we aimed to establish the framework and the scope of the SRI's integration into the dynamic EPC. And we've tried to develop actually the required procedures and the guidelines that need to be realized in order to have an SRI certification based on the linkage of EPC data, and in a mandatory way. So every time an EPC is conducted, we have also an SRI certification as well. We have to do that, we follow a 3-step methodology approach. We perform a very detailed overview to see what is the current status of the SRI, what are the methodologies, what the issuance procedures, and also the legal framework. And we did that by performing an overview of the official SRI documents that are currently available. Then we identify and extract the building automation control data that is needed for the issuance of the SRI based on the EN 5-2000 standards for EPC issuance, as well as based on the BIMA FC4 schema. And we resume with the guidelines and the guidelines for the SRI integration in D2EPC. We developed the minimum requirements for BIM modelers as to be offered to the EPC assessors, and also we conclude what is the challenges and the limitations we identified during this process. Yes, concerning as I said in the second step, we perform a mapping of the SRI input data in accordance to the EPC methodology of EN 5-2000 standards, and we also perform a mapping of the SRI building automation control equipment in IFC4 schema in order to identify if the functionality levels can be adequately defined in IFC. As you can see here in the flow chart, we have a BIM model, an IFC document, and we identify which SRI data included in the IFC schema, which can be defined and which are not. And these also be used as an input in the D2 EPC platform and to deliver the SRI indicators. We did that. We selected the method B of the current SRI methodology, which includes 9 domains, as I showed before, but also in total 54 services. You can see here in the list which service, how many services includes each of the domain category. And we identify the input data, the metrics that required for the SRI assessment to be used in the D2 EPC platform. Another challenge we have to face is also to investigate whether the SRI data which are included in the IFC can be defined, if they can be adequately defined, this is the level of completeness. In order to do that, we define 3 different categories to describe this level of completeness. The first is a complete category, which means that the equipment and controls and relationships can be adequately defined in the IFC. And a partial, which equipment or maybe some relationships cannot be defined adequately, and also not supported, which is the SRI data which couldn't be defined in any case in the IFC. For example, the EV charging is one of these categories. We needed to split the functionality levels in different hierarchy levels in built-in automation and control. So the first level included the field level equipment, the sensors, actuators, and other physical, let's say, devices. And then we have the automation level and then the management level. So each one of these functionality levels represented has 1, 2, or 3 different categories. Here you can see an example for lighting. We found out first the metrics for each of these functionality levels, what type of equipment actually means. So we have some manual, for example, switch on, switch off for lighting. We have some occupancy sensors, etc. So we identify the equipment first, and then the metric data was used to map the data with IFC entities enumeration. This is also an example of the lighting. For example, this lighting switch was under the IFC distribution element, and we found the IFC switching device. As a conclusion, we did that to every one of the domain of the functionality levels. And what we found out that for the first point, and I didn't mention it a lot of times because it was actually easy, that the current status of the EPC 2EN5 2000 standard does not allow the extraction of the SRI, so we didn't. This was a very brief conclusion from what we see. We cannot have enough data, of course, and can only be extract some basic mechanical equipment types of the building, as you can see here in the list. Concerning the SRI, we found that at this stage in the IFC schema, there are a significant number of functionality levels which are not be addressed or cannot be defined in the IFC schema, which also didn't allow a very comprehensive approach for the extraction of the SRI based on the IFC. We concluded that the information currently supported in the IFC is mainly based on level 0, level 1 of SRI equipment, which is basically field level and maybe some physical devices and wire relationships. And while there is this is highly fragmented and vendor dependent, let's say, for defining some more logical operational aspects concerning the last management level, such as configuration management and other. So we have the we could also extract some basic information based on the IFC in a larger extent than based on the EPC input data. You can see here is on the list. And with this information, we could define the minimum modeling requirements that could be used in D3PC for the extraction of the first layer for formation for SRI. So this could be used as an activating process in order to have the rest of the calculation procedures in the calculation engine of the D2PC platform. So indeed, we have also need some user-specified features as well, as I said. Yes, this was the conclusions, and thank you very much. I think also this concludes the first session, so if you have any questions for me or the other colleagues, we'll be happy to answer.
Thank you very much, Christiana. Indeed, we have concluded the session 1. We are a bit ahead of the schedule, so we have plenty of time for the discussion. Yeah, Panagiotta, will you lead?
Yes, yes. Thank you. There is actually one question in the chat for the first sessions. This is addressed to Carlos from the Minister project. So you have a slide. I was actually thinking about the same thing. You have mentioned that we don't have high energy thermal storage in our houses, and some obstacles are relevant to technology, price, regulation, or consumer acceptance. So which one of these is the biggest challenge that you have, and maybe how you plan to tackle it?
Yes, thank you very much. Yes, it's a very good question. Actually, I think one of the biggest challenges is the standardization, because it defines many of the elements that have to be used. For example, in our case, and as one of the people in the audience is asking, ammonia can be dangerous, but then of course we have many dangerous elements in our homes, and we are just using them freely. So the technologies exist, but they have been used mostly in industrial settings. So this type of standards, they also define that it has to be used in a sort of standard setting. So when you try to translate it to a residential one, then you have a scaling problem, because you need things that must be smaller, that must be user-friendly, that do not need so much high maintenance. But on the other hand, we also have new technologies, for example, automation. We have high-performing welding systems that can, in a way, try to make this system more usable inside homes. So at the same time, this also influences the other factors, for example, the acceptance of people, the technology developments, and also the price. Because if you see that it's too hard, that it's too complicated, then people might not accept it, then it's too expensive, and then there are fewer investments on this technology. So I hope this answers the question. And then for the second question from Angeliki. Yes.
Yes, sorry, I was muted. Thank you, Carlos, for your feedback. Indeed, there is a second question about the gaseous ammonia. If you can elaborate more about this toxic compound and the relevant legislation.
Yes, as mentioned, there is no exact legislation about ammonia. It's more standards. It's the EN 378, which is divided into 4 different parts, and which regulates practically all the known refrigerants. As some of you might remember, ammonia was used in the very early stages of refrigeration. But of course, because it's very toxic and the technologies for containment were not that good, it was discontinued towards the the gases that were used from the 50s until the 80s and 90s. So the ammonia that is used is the minimal amount that is allowed by French legislation, because one of our partners is French and he developed the system, which is almost like 50 kilos of ammonia, more or less, which is like a small tank that you can find, for example, for oxygen, for propane, etc. So this is the less energy produced, but also the system is not releasing any ammonia. The ammonia is circulating all the time inside the system and never goes out. So this is another of the challenges we found from the standardization, that the standards are geared for refrigeration and not thermal storage. So also we have to see, and we're going to test it in the project, how this behavior is done in a practical setting and how it's regenerates, because the system is used in smaller amounts for refrigeration of mobile containers, for example, for medicines, for food. So it has been proven and it has been safely operated.
When does the project end, Carlos?
It will end in the middle of 2024.
Okay, so there is still a lot of work to be done. So maybe we will have more results and findings on the discuss issues in the next years. Okay.
Yes.
Thank you. Are there any other questions? I don't see anything in the chat, but you are welcome to write if something pops up, and I believe we will have time to revert to that if needed. I guess we can proceed with the second session.
Yes, if there are no questions, then let's go to session 2. So integrating human comfort into energy certification. We're starting with our first presenter, Justas Brazauskas from University of Cambridge. So you have the access to share your screen and you can start with your presentation.
Yeah, just a second, please. Got it. Oops. Sorry, way too many buttons.
No worries.
All right, you should see my screen now, right?
No, we don't see it. We saw it before, but
All right, maybe, can you see it now?
not yet. No.
Oh, I'll just do it again, no worries.
Yeah, that's perfect.
Okay, should be fine. Yeah, first of all, thanks so much for having me. All of this is kind of work in progress, so apologies if it's not exactly finished, and we don't have exact conclusions to draw on from this because we just started working on this a couple of years back. The things that I wanted to talk with you today was how this densification of sensors in buildings can impact well, buildings inhabitants, and how these buildings in return can see people in a way that ourselves, like, we can't see it through our breathing and just sitting in rooms, and how we can infer where people are in the building that we couldn't do otherwise without this densifications of sensors deployed in these smart buildings or smart environments. I refer to this as smart environments because the same technology stack that we have deployed in our buildings can be deployed on trains, on ships, or any other environment that has the capacity to be kind of can host multiple sensors like CO2 or temperature. Okay, so that brings me to the contents of this presentation. So first of all, I just wanted to go through the context of how we do work in our lab related to BIM and IoT interoperability. Then I'm going to talk about how we have our own little test bed in our computer science department in Cambridge and the sensors we use and the platform we built. And then I'm going to go through a sample, a couple of slides that just describe how our deployment happened at a smaller scale. So I'm just going to focus on a single lecture theater rather than the entire building. And then I'll quickly just discuss how these sensors can actually influence people and how we can use the collected data to visualize human activity in the building in novel ways that haven't really been seen before. So our primary work relates to the adaptive city platform that we have created a couple of years ago. I believe the work on it started in 2020, so exactly when the pandemic happened, actually. And it was quite surreal working on smart environments or smart buildings, being so detached from them. So we deployed a lot of the sensors in our department, and then we physically couldn't go there, so it was quite a challenge. But in general, what we were trying to do was to connect BIM, BMS, and IoT data into a single unified system, right? So to have the building metadata, the temperature from BMS systems and IoT devices into a single platform. However, our building was quite old. It was over 20 years old, so we didn't really have the most advanced BMS on the planet. It was still running Windows XP, so we soon realized that we had to drop it off our research. And then what happened was just BIM and IoT interoperability. And the goal of this was to combine multiple data sources, right? So we have kind of low frequency, low granularity BIM data, right? So floor plans and 2D and 3D reference data. And then we have our high frequency, high granularity IoT data that's just spamming information every second from hundreds of sensors deployed in the building. And it was a challenge on how do we actually combine the two with flexible APIs and ways to visualize it to the end user so that everything is understandable. So the starting point was selecting the right sensors we wanted to deploy. We have installed over 300 sensors. I believe I have the exact number in a later slide in our building. It's our department building. It spans 3 floors, and it's a combination of research offices, research labs, and teaching spaces, as well as a small cafeteria. So it's a rather massive building. And for the sensor that we used was mostly ELSYS, just Swedish sensor manufacturer sensors. They're all LoRaWAN based, so we have a long battery life. And it was a combination of CO2, temperature, humidity sensors deployed all over the building. So the platform's web interface is rather simple. It's just a website you can go to. And we decided to have kind of larger research interest displayed there. So we have our about tabs, research tabs, project tabs, and then the core of the platform lies in the lower 3 cards, so where we have space sensors and data management. So it's quite convenient because we can look at the floor plans of our building, or actually multiple buildings, inspect all the sensors, all the sensor data and time series data. And using the data management tab, we can just completely change things around, move our sensors around, modify the metadata, and it's really easy to do. You don't have to log in some remote database and try to change things there. You can just do it on the web, which is very convenient for us. When clicking on the space card, as on the slide below, you're immediately taken to the map view where you can select the building you're interested in. So as I said, the initial deployment happened during the pandemic. So instead of deploying all of the sensors in our department, some of them ended up being deployed in researchers' flats, right? So we had a couple of smaller smart building deployments where people just work from their homes and had to transform their flats into smart environments. So you select the building that you're interested in, and then you're taken to the page that you can see on the right. So you have a floor plan and then a bunch of circles representing the sensors deployed in a specific room. You hover over it and you kind of get a snapshot of the most recent readings. So we have temperature, humidity, CO2 that's available. And here there's an 8x8 grid. It's because this particular sensor had an infrared camera. So this is actually showing what the camera is looking at. It's a very low resolution camera, but you kind of see that I believe it was pointing at a person sitting in front of a monitor or something. So you can see that a person is there and they're working on something. And then if you click on a sensor, you're taken to a time series view where it shows temperature, humidity, or CO2 readings on a graph, and you can compare several readings at the same time. So you can see, for example, how CO2 correlates with temperature or humidity and that sort of thing. So it's quite convenient. So just to describe how all of this was done, we took our floor plan building information, so it can either be BIM-based or SVG-based. As I said, this particular building happened to be quite old with no BIM files, so it was not a BIM native building. So actually we ended up just parsing our SVG files to create a kind of virtual building representation using our ontology of choice. We could have done exactly the same just by parsing BIM IFC files and then converting into our virtual ontological representation. We looked into using several ontologies, but we soon found out that using any sort of linked data tools available on the web, we can easily convert from one ontology to another, for example, from brick to something else. And we just decided to kind of keep away from it until there's a single ontological standard that's available worldwide, rather than using 20 different ones. Then we used our virtual building representation to generate the SVG that's available on the computer screen, just by using API requests, and then we draw the floor plan and sensors on that generated floor plan that was generated from the original floor plans. So it's quite a difficult process to go through, but then what it does, it gives us a lot of flexibility, especially when we have multiple buildings available. We can just use the same pipeline to just insert different buildings with different BIM standards or without any BIM tools available, and just get it available on the platform. So what we've done, we have over 453 sensors deployed over the 3 floors of the building. We have a real-time data processing architecture, so whenever a sensor is triggered, it takes less than 100 milliseconds for that reading to appear on screen. And as you can see, you see these little splashes appearing on screen in different rooms, and that is these sensors being triggered in real time. And then you also see this heat map that's overlaid over individual rooms. So instead of just kind of having to move your mouse over a sensor, we just show it on a heat map on screen, so it's quite immediately obvious which parts of the building are cooler or warmer, or what levels of CO2 are available. And I'm just going to go back to this real-time part really quick, because it's quite a game changer in the way we interact with these buildings and the way these buildings actually see us. So for example, we have a corridor where I've deployed a bunch of sensors on the ceilings, and every single one of those sensors has an infrared camera looking down the ceiling, right? And this is especially cool because if someone is walking down the corridor, these sensors get triggered one after another, so we can see movement happening in real time as people traverse the building, which is especially exciting because you don't have to wait 5 minutes for sensors to send their data, and there's no artificial latency introduced in the process. So now, for the purpose of this talk, I'm just going to quickly focus on the deployment in one of the lecture theaters, because to focus on the entire building, it takes a bit more time than just 15 minutes. And I'm just going to focus on a small deployment we did in September, I believe, to see how CO2 levels change whenever there's students in a large lecture theater, which was especially important in the backdrop of the pandemic, because one it monitors CO2 levels and see if the environment became unsafe for students at any point during lectures. So that's the lecture theater we selected. It's quite large. I believe it can host over 100 or 150 people. We had to take precise measurements of the lecture theater. We had to check that the network connectivity was sufficient, which was especially important because if the LoRaWAN network connectivity wasn't strong enough, our sensors wouldn't hold their battery life for several years. And it was quite essential because once you have that many sensors, you don't want to be running around and changing their batteries every half a year. So after having some field work done, we went ahead and bought over 50 LSys sensors. All of those had to be calibrated and prepared for deployment. Another part was actually deciding on how to best deploy these sensors in the lecture theater. So there were several combinations of how we could actually do it. We went to the one that had these sensors placed in the most equidistant way, so that we'd cover most of the lecture theater and just wouldn't have any sort of black holes, so to speak, where we wouldn't have any readings available. And then it was actually deployment time where professors shamelessly use PhD students to do all the hard work, and we had to go in and deploy a bunch of sensors under desks and over various corners of the lecture theater, which was rather uncomfortable for our backs, but had to be done. Then we had a coordinate grid over the floor plan to get the exact coordinates for every single sensor, so we'd have precise metadata readings, so that we connect that to our platform so that all of the sensors would appear in the right positions on the screen. And once we did that, sensors started sending their data, and as you can see in the GIF in the bottom right corner, everything was working fine, so it was quite exciting. And then a couple of interesting results started arriving. So for example, we see that in different parts of lecture theater, we have different time series plots for the same time. So for example, where the lecturer was standing, just happened to be speaking more and possibly exhaling more CO2, then CO2 levels in that particular place was a lot higher than somewhere else in the lecture theater where there were few students sitting. So what also had to be done was, instead of just being able to inspect individual sensors in the lecture theater, we had to average out all the readings, so you could have combined the readings for the entire room, right? So so kind of average out readings for the entire level, for the entire room. And when combined with our heat maps, this provided very interesting results. So what we also did was so we could inspect these fine granularity differences between readings in different parts of lecture theaters. Obviously, time series data would not be very sufficient, so we used our heat map algorithms over this lecture theater. And you can see how different parts of lecture theater actually have substantially different readings. And oftentimes it actually relates to where people were sitting, as seen in the pictures below. This was also rather time consuming because we had to go into every lecture and take photographs from the back, and then with the dots on the floor plan where people were sitting to preserve privacy and everything along that. So here you can see CO2 levels during 3 different lectures. And what we found out that since the lecture theater was at an incline, CO2 tended to build up at the back. And even though CO2 is actually heavier than air, and it should not rise up, the fact that it's being exhaled from the human body means it's warmer than the surrounding air, and then it does go up and tends to build up at the back of the lecture theater, even if there's a massive incline there. So these were a couple of very interesting findings to look into. Another example was student sitting positions and temperature distribution in the room, and here it was a bit more problematic, and then it came down to how we actually calibrated our sensors and what we wanted to use them for, because there's quite a bit of noise, which I'll get to in a second, and quite a few inconsistencies that happened because of some sensors being misplaced. So you kind of see some correlation between where students were sitting in parts of the lecture theater that is warmer, but it's not that immediately clear. And then we wanted to run a study to see how these sort of data visualizations on our deploying sensors could actually influence buildings users, right? So we came up with 3 different ways to actually visualize all of this. So far, you've been seeing the visualizations using the color scheme that is in the middle called B. And I'll show you a quick video of CO2 levels changing in a lecture during the span of a lecture. So there's a little clock at the top. It shows real-time clock time, right? So the lecture starts, I believe, at 10. So our recording started at 9:30. And there's a time series plot below with 2 vertical graphs showing where the lecture has started and where it has ended. So the time series graph is showing averaged out readings from the entire lecture theater, as I've talked before, because we didn't just want to select a single sensor because that would skew the readings. And we are comparing just 3 different types of visualizations and how they represent the same thing. So the ones on the left, so A and B, are showing a CO2 accumulation, and then the one on the right called C, it's just showing the CO2 rate of change. So there's different ways to represent the same thing. So yeah, we start at 9:30, and then there's a floor plan kind of overlaid over the lecture theater to better see where everything is. So what's interesting is that the CO2 starts rising very, very rapidly within 15 minutes, and then it almost plateaus, right, as the ventilation system kicks in and just doesn't seem to be able to hold up with your ambient levels of CO2, so it just reaches a plateau point and then just stays there. And then CO2 just starts going down quite rapidly after the lecture is over. I'm going to play this again because it's rather quick. And it's hard to see things the first time. So for the purpose of this visualization here, we're trying to see which one worked best and which ones the building users preferred. And then we ran a quick study to see that people actually prefer the one that was in the middle with the green color scheme. And just to confirm our hypothesis, right? Most of the people asked that they would use it frequently, and then they found that the visualization was able to aid them to select where to sit next time. So you kind of have a different level of sort of human building interaction happening, where our identification of sensors is able to start this feedback loop that tells people where to sit next time, so that they can move to a different place, and then you can look at the visualization again and see if they were happy with CO2 levels there. So it's apparently safer for them to be that way. And this was very exciting, actually, because we weren't sure if people were going to like this, or maybe they'd be freaked out by how the building is actually tracking them. And to our surprise, everything worked fine, and people were definitely okay with these sort of measures being taken. Now, to finish off, I just wanted to discuss several challenges and drawbacks that happened during the deployment. So first of all, as I mentioned, there were some inconsistencies in some of the heat maps shown, especially the temperature one. We looked at the temperature heat map for many hours, and we saw that some spots were consistently warmer than others without any possible explanation. One possible explanation was that when you're deploying over 50 sensors at once, you want to make sure that you calibrate them all under similar conditions. But once you have that many sensors, it's kind of difficult to do that, because you want to sometimes do it in batches because you either don't have enough time, or it's just too big of a job for a small group of students to do. And what happened was either it was a combination of us not calibrating them correctly, or they were miscalibrated from the factory, or as in this one instance, one of the sensors was placed on a sill next to a glass window behind which there was a projector. And then close to that sensor, there happened to be a small router, right, that was emitting a lot of heat. And we didn't notice that before, but it was emitting so much heat, in fact, that it just queued up the entire readings for that one single sensor. And it was only over when we moved the sensor a couple of 20 centimeters to the right, so that it wasn't impacted by the heat emitting source anymore. And it seems like a silly thing not to notice, but there are a lot of these things that just kind of go behind your head when you're deploying that many sensors at once. Another thing was a bunch of HVAC ventilation spots on the floor, where you had constant airflow that was possibly messing up our CO2 levels. And things like this are kind of hard to overlook, but at the same time, you can't really ignore it. You can't avoid all of the possible HVAC locations, and you just have to learn how to do some signal processing to overcome it. Another thing was kind of sensor calibration, but in a different way. When we deployed our sensors, as I said, we did it in batches, right? And some of the sensors may have been miscalibrated in the temperature domain, which again is a bit of a issue when ideally things like that would be done in a factory setting in a controlled environment. So it's not really our misplay, but rather the manufacturer's fault, I believe. So what you can see in the middle, we have the heat map that we used, and you can see several bright red spots. that somewhat aligned with where the people were sitting, but not really. As you can see, two big blobs on the left and two big blobs on the right. And then there is a massive blob in the middle, right here, which kind of corresponds to where people were sitting, but we're not unsure about the two blobs on the left and right. And what we did, we actually subtracted midnight readings from whenever the lecture was taking place, so that we kind of have an even baseline to account for all the center drift and miscalibration. And then what happened was this image in the middle, the blue one, where the ambient temperature readings actually matched where students were sitting rather well. And it confirmed our suspicions that a lot of the noise was because of sensor miscalibration. And then we also experienced some difficulties with network connectivity, routers going down and not working. So there's a lot of going back and forth and making sure everything works. Finally, ethics is a major part of this, and it's another can of worms. I don't think we have enough time for this short presentation, but it's very important to make sure that all the data is collected and stored safely. If you'd like to read more about that, we had a short BuildSys presentation last year. Here's the paper, and then have a couple of preprints in the work, so you can check out these that have better description of the software that we're using and how we actually deployed everything. So thank you so much for listening to me, and I hope you have any questions. Thank you.
Thank you, Justus. This was a very interesting presentation. You did a lot of interesting work. But let's move to next one. It's Vivian Dorizan from iBroad EPC project. You are muted. Yes.
Hello, everyone. Good morning. Can you hear me?
Hello. Yes.
Okay, let me share the screen and put it in presentation mode.
Yeah, that's perfect.
One second. Hey, everyone. Hello. My name is Vivian Dorizas. I am from BPAE. Many thanks for the kind invitation. I have a lot of comments for Justus' presentation that was just before. Just to tell you a bit of, I also have a strong background on monitoring, so Justus, I may have lots of questions regarding the instruments you use and all of that, but I will come that in a while when I will explain to you about the project. So I will talk about the project iBroad to EPC that we're currently working on integrating building renovation passports into EPCs for a decarbonized building stock. I should tell you that this is a project that comes right after the iBroad project, which was the first one in which we developed and tested and delivered a model for a building renovation passport that supports single-family homeowners with personalized advice to facilitate stepwise renovation. And the iBroad to EPC project builds on these achievements of the iBroads and broadens the scope of the concept and adapts it to the national EPC schemes to prepare the rollout of next generation EPCs in 6 different countries. So to start with, we all know, I guess everyone in this following this presentation knows the importance of indoor environmental quality and ensuring adequate levels of indoor environmental quality, including thermal comfort, air quality, lighting, and acoustics. It's a really crucial and very important, because it affects human health, and should be a driver for building renovation and construction. However, indoor environmental quality is not covered into the EPCs, and by integrating building renovation passport elements into the energy performance certification, which is proposed by the iBroad to EPC project, then the reliability, usefulness, and the effectiveness of the EPCs is improved, and comfort aspects are taken into account. Of course, the renovation is a challenge, and especially if we're talking about a step-by-step renovation, there are several barriers here. First of all, there is an uncertainty and lack of knowledge. The homeowner doesn't really know where to start the renovation process and which are the measures to implement, into which order they should implement. It's quite a complex process, and it really is combining loads like the ability of the workers. Is difficult to access finance. There is a lack of awareness on the financial support. There is an insufficient of training of the auditors that I mentioned before, and it's a very complex process. And of course, there is also a limited follow-up after the energy audit or the issuing of an EPC. And there is no quality control mechanism of the certification of works. So really a plan is what can really help looking into the renovation process from a holistic point of view, and the building renovation passport can be the solution to that. And why we're talking about a building renovation passport? Because with the building renovation passport, the ambitious climate targets are implemented, and accordingly, each renovation must contribute to reaching the climate target. And with most building owners carrying out a partial renovation over a certain time span, and when these are carefully planned from the start, so as to build on one another and to avoid lock-in effects, the renovation steps can enable deep renovation that is achieved for a long-term horizon. Also, an overarching plan provides guidance about which components to renovate, when and how, and at which cost, and which are the savings that can be for the building owner. And of course, a long-term plan can take foreseeable occasions in the homeowner's lives into account. So these are the two products that were developed from the IB Road project. As I mentioned before, the project that the IB Road to EPC is built on, which is the building renovation passport. Is a combination of two concepts: the renovation roadmap and the logbook. The renovation roadmap delivers a long-term renovation plan for individual buildings through tailored advice to homeowners and investors to contribute to the achievement of the long-term vision. And the logbook is a repository of the building information going beyond energy performance that can include features such as design plans, the actual energy consumption, the maintenance requirements, and also include some legal documents as well. Here you can see the main guiding principle for establishing the roadmap. We have the best possible principle to propose the measures with the highest possible energy efficiency, the individual renovation context that takes into account the needs, the financial situation of the owner and the inhabitants, the long-term perspective to help the homeowner understand that we're talking about a long-term planning, a long-term strategy, that things will happen at a step-by-step process, not everything at once. The time and sequencing to demonstrate to the homeowner the benefits of the planning and to the step-by-step renovation that I mentioned before. And of course, it's important to make that attractive and motivating. In addition to that, on the general objectives of the project, the IB Road to EPC aims to contribute to the establishment of next generation EPCs that make them capable of supporting the deep renovation of European buildings. And this will be achieved by upgrading the EPC skills with the integration of elements of the building renovation passport. And so we have here the EPCs, all of you know, which are at the different levels developed in the different member states. And with IB Road to EPCs, we're aiming to include aspects such as the IQ and the SRI that was mentioned before, and provide customized recommendations for deep renovation. Renovation recommendations are aligned with the long-term energy target of the specific countries. They will be tested in single-family, multifamily, and public buildings. And here you can see some of the general objectives for the project. But so why am I doing this presentation? So I started by describing a little bit of the project. What is the project about? The IBRO2 EPC. Now the crucial thing is how we can integrate with the within EPCs the comfort aspect and why is comfort important? The comfort is important because people are spending a considerable amount of their day within indoor environments, and there are several benefits of the renovation, such as health, well-being, economic, physiological, and even productivity. So I will talk to you now about a tool that we developed within another project, which is called Extendo. Some of you probably already know of that, which we are aiming to use parts of that tool within the IBRO2 EPC, of course, adjusted to the needs of the building passport and to the needs of the specific project. And here are the challenges that we faced when developed the comfort feature for Extendo. First of all, was the cost and the time, because the plan was to integrate this comfort feature within the EPCs, and of course the time required to have a proper how can I say, approach and evaluation for the comfort. Some monitoring is required, but of course this requires some time, and the time increases also the cost. So all these were challenges that we faced on whether to on the timing of the measurements of the surveys, on which exactly building to building or zone to use, what exactly to measure. For example, we couldn't do like a detailed monitoring as just presented. It should be something simpler and easier. So how we developed it? First of all, we tried to make it flexible and adaptable based on the different building typologies, domestic and non-domestic. It was based on these four main indicators of the thermal comfort, air quality, visual comfort, and acoustic comfort, which are the main parameters of the indoor environment. And also we came up with individual scores for all indicators, or either a combined rating that would combine all four indicators mentioned above. And what we had in mind always on the development was to make it affordable and time efficient as well. So the approaches that we used were these three different approaches: the measurements, the checklists, and the surveys. On the measurements, we had to define a specific monitoring period, the building level parameters. On the checklists, we had building materials and systems that the EPC assessor would go to the building and check and see whether the buildings had the specific materials or systems installed. We would do a visual inspection, for example, for the identification of mold, a space, and then the function of the space, and then the surveys were to the building occupants on their perception, satisfaction, and acceptance, and then of course on their activity and the level of control over the indoor environment. For example, if they would have access on the thermostat, etc. And we came up with two different ratings. The one was the operational rating, and the other one was the asset rating. The operational rating concerns buildings at operation where occupants are involved, which is a bit more complicated version of the assessment because it requires measurements, checklists, the surveys, and measurements winter and summer. For example, ideally 1 week in the summer and 1 week in the winter. While the asset rating, it's more simple. It only requires the checklists that the assessor goes and does a quick review of that, of the building. As you can understand, of course, the operational rating is much more detailed. This is what we recommend. However, we understand the restrictions, for example, on the EPCs with regards to time and the costs. And therefore, we also came up with the asset rating that can also give a general overview of the indoor environment. And here you can see the visualization of the results. First of all, we define the weightings for the 4 different categories, and then the average score of the 4 different ratings is visualized like that. And this is quite a flexible tool because it gives the flexibility to the user to either use all of the indicators or select a few. For example, some of the member states suggested that for us, for example, thermal comfort is more important. We only like the scoring to present the thermal comfort. We wouldn't be interested on the rest. So he would be able to present, to tick off the air quality, visual comfort, and acoustics, and then just move forward with the thermal comfort. However, our suggestion is to keep all of them. So this is how it looks, and the plan is to take into account to keep what is important for the IBR02 EPC project and base the development and integrate the comfort aspect of the IBR02 EPC, but of course adjusted to the needs of the specific project. Just to let you know that this is a team of 12 organizations from 9 countries, and the project started last September. And we also have our coordinator in the call, so if there's anything that you would like to add, also Alexander, feel free to jump in. That is all from my side.
Thank you, Vivian. Again, questions in the chat if you have any, and we will discuss them in the question and discussion section. And we can then continue with the last presentation in session 2. Again, this is one of the partners from D2 EPC project. So Thanos Kalamaris, you can start your presentation.
Hello, everyone. Can you see my screen?
Not yet. Yes.
Okay. Okay, perfect. Okay. This presentation concerns the human comfort and well-being indicators analysis that will be incorporated in the D2 EPC. It dives a bit more compared to the very nice presentation that we already had the chance to see from Vivian. In brief, I would like to refer to the objectives of the D2 EPC in regards with human comfort and well-being. We begin from the user behavioral profile extraction that influence the building's dynamic performance from the scope of the occupant's comfort and well-being. These profiles correspond to preferred operation, preferred by the end user operation, which is expressed through specific boundaries, which we want to extract it straight from the end user's past data. Furthermore, the D2 EPC incorporates a set of human comfort and well-being indicators that will be built upon these profiles, and further incorporate them in the building assessment scheme. And further, within the D2 EPC, we wish to examine those limitations of the defined KPIs in relation to the building's operation. And lastly, through our web platform, provide information to the end user for the indoor ambient conditions and the progress in regards to the comfort and well-being of the space throughout the years of the certification participation in the D2 EPC of the end user. For concerning the human comfort and well-being framework that is constituted in the D2 EPC, In our case, 3 indoor environmental quality pillars were considered: the thermal comfort, the visual comfort, and the indoor air quality. For the behavioral comfort profiles extraction, a measurement-based approach is utilized to be performed on the building data streams coming from the pilots. These personalized boundaries, as I mentioned before, are calculated based on the user's previous behavior, trends and patterns in the temperature data set, for example, with the usage of a specialized comfort profiling engine, which will be delivered by the Hypertech Energy Labs. In this way, we wish to calculate these profiles in a dynamic, purely data-driven, and most importantly for us, at least, non-intrusive ways, in order to avoid as much as we can the interference of the occupants and to request as less information as possible. Lastly, for the human comfort and well-being indicators, we wish them to be based on well-defined and measurable environmental performance metrics, and this is pretty critical to us because taking into consideration the budget, we wish to deploy relatively cheap and widely available IoT equipment. And these performance metrics combined with boundaries, the comfort profiles, and some long-term evaluation methodologies, which I will refer later. This constitute our indicators. In DTPC case, we utilize a hybrid approach for the profile extraction. As mentioned, this engine is utilized to calculate thermal and visual comfort profiles based on the end user data, subject to the data availability and quality, of course. And in cases where this is not possible, either there is no data to do so, or some other environmental metrics that are not relevant with personalized extraction, a literature research has been performed in order to extract recommended boundaries in regards with all these environmental metrics selected. And these boundaries, combined with real-time data, are further streamed to this calculation engine that we will develop in the scope of D2EPC, and this calculation engine will deliver the calculations of the respective KPIs. A brief overview of the literature that was considered and researched. Within D2EPC, we heavily considered the levels framework, which is a relatively new framework delivered by the European community. In our scope, the 3 indicators as called within levels were considered: the indoor air quality, the time outside thermal comfort rates, and the lighting and visual comfort. Furthermore, some standards that are included in the levels have been further researched in order to check which environmental metrics should be selected and which evaluation methodologies. And these long-term evaluation methodologies translate these metrics into indicators. This is how we go from a mere measurement, a metric, to an actual performance indicator. To provide you some context, the time out of range calculates the percentage of hours during which the comfort of the occupants was outside these predefined boundaries, either extracted from the user or the literature. The degree hours takes this calculation a step further, adding some weights in order to address how much the indoor ambient conditions deviated from the recommended conditions. And these weights are defined based on the absolute difference between the measured value and the upper or bottom boundary. And lastly, we have the footprint of the indoor environment, which reports the percent of hours of its level compared to the total of hours of the period of interest. And this last evaluation methodology is more relevant for the indicators that are constituted on specific limits categories delivered by the literature. To dive into the indicators, in the thermal comfort case, five indicators have been formed. The environmental metric that was heavily considered due to the fact that they're well defined, they're measurable with IoT equipment, and that will be either deployed in the pilots or is already accessible from existing installations. So we heavily considered those two parameters, and we attempted to extract as much information, the maximum information possible from minimum sources available. Because, of course, if you have access to more information, other metrics, you may be able to deliver a more defined and fine-tuned result in regards with thermal comfort. But we try to be realistic and see what we can do with what we have. And this there are further than the environmental metrics. We examine also the combined effect of the two, delivering two thermophysiological parameters that I'll show you some results in the next slides. Regarding the visual comfort case, the only environmental metric that was considered well-defined and measurable and suitable for inclusion was the indoor illuminance. We utilized the evaluation methodologies to define a set of indicators for the visual comfort, and the boundaries were either extracted from the user's data or especially the standard 12464 delivers some limits, some illuminance limits based on different activities in different space typologies that will be considered in order to calculate these indicators. In the air quality case, the levels framework was heavily considered, especially in this case. It delivers a plethora of environment and in air quality metrics of gas concentrations that are considered harmful for the human respiratory system. In this case, this techno-economical feasibility analysis that we performed in regards with the D2 EPC pilots and the equipment that can be deployed actually, the main focus will be made on three specific indicators: the CO2 outdoors, the total volatile organic compounds, and the particulate matter of 2.5 diameter. The rest of the indicators are a bit more sophisticated as measurements and require either multiple installations of IoT equipment, and they have been incorporated in our framework. If in some cases for some reason they are already measured within a building. A few words for the personalized comfort profiling engine. As stated before, it analyzes the collected data from the pilot infrastructure and identifies these occupants' comfort boundaries. This approach is based on the fact that we imply that the optimal visual and thermal conditions of the occupant are dictated by him or herself. So this the behavior is imprinted on previous data. So we manage this way to extract insights exclusively from preceding time series data, with no other sources of information required, such as surveys, etc., that we consider it at least as hypertech, intrusive to the end user. And this, the engine comprises of state-of-the-art classification algorithms. Have considered the SAX algorithm. It is worth mentioning here that we have two different versions of a personalized profile engine. The first one is contained a probabilistic model that is based in implicit or explicit events. So the actions or the absence of the action of the user combined with the temperature, with the sensors measurements are given as input to a probabilistic model to infer which temperatures are characterized as comfortable. This, though, expects some more information, and it has the control commands from the end user. So this is one more information required, and since we try to extract maximum information for minimum resources, we used these clustering algorithms with performing some dimensionality reduction and define some levels of user preferred operation in regards with air temperature, for example, in order to narrow down the the boundaries delivered by the literature, which as I will show you in the next slide, are considered relatively wide. So I have some preliminary results from some test data in an occupied living room. As you may see in the graph, there are events of temperature and relative humidity measurements aggregated on an hourly basis. So the granularity of the measurement was lower, and there was an average on an hourly basis. The four regions recognized within the graph correspond, beginning with the red dots, to discomfort events in the heating period. The yellow patch is considered as the no discomfort area for the heating period. And from the temperature of 22 degrees, we may utilize this Humidity indicator, which expresses the combined effect of temperature and humidity in the human comfort. So we may see here, if you observe this, this slope corresponds to the fact that with higher relative humidity values, then with the rise of the temperature and the higher relative humidity values, we generate discomfort for the end user. And so these black stars correspond to these events that could be characterized as some discomfort for the end user. And I have some indicative results from the thermal comfort case. This deviation from the temperature range was calculated on the standard ASRAE 55 standard for the boundary of air temperature for recommended operation, and the thermal degree hours as well. The humidity range corresponds to the boundary corresponds from 30 to 70, and which is this indicator is a combination of the two. It addresses both air quality and humidity, because high humidity values end up in thermal discomfort, and low humidity values ends up in dry eyes or maybe some respiratory implications. And lastly, the humidix levels showcase that actually these measurements that we extracted from the living room of the during occupied hours correspond to no discomfort at 92% of the time. That's for my part. If you have any questions, I'll be glad to answer them. Thank you very much.
Thank you, Thanos. With this presentation, we have also concluded the session 2. So now it's time for questions and discussions.
Yeah, thank you. This session raised some questions indeed. Let's start with Eustace. I think that most of them have been briefly answered in the chat, but we can discuss a little bit more. There was a question for you, Eustace, about the sensors that you used for the monitoring, and if you can elaborate more on that and what measurements were actually taken also.
Yeah, it was a bit of a long trip to get the sensors we ended up using in the end. At first, we thought of using our own sensors, just kind of making Arduino sensors and then just deploying them, but we soon found out that at the scale that we needed these sensors to be deployed at, it just wasn't going to be possible. So then we found those ELSA sensors, and then we had a lot of discussions about the sensors we wanted to look into. So obviously, most of the sensors on the market, they're focusing on temperature and humidity, and then some of them have CO2. But then as soon as we started deploying our sensors, and then when the pandemic began, we realized that CO2 was by far the most important measure we wanted to look into, because as soon as someone enters a room, right, temperature is going to become warmer after an hour or so. It takes a while for the temperature to heat up from the human body radiation, and same applies for humidity. But with CO2, right, when you enter a room, CO2 levels start rising very, very rapidly. You can see like it just goes up within the first 5 minutes to a noticeable degree. And then we found that for all the future research, we want to make sure that our sensors have CO2 sensing capabilities. And that is why we settled on those ELSA devices that I have described, and I have a link in the description. I'm pretty sure there are other manufacturers. It's just that the ones we selected, they had decent customer support, and they were LoRaWAN equipped devices. That was very convenient for us.
And what about the cost of the sensors and the lifetime of the batteries?
So lifetime of batteries depend a lot on how often these sensors actually are configured. So how often they send the readings. They can be sending the readings every 10 minutes, half an hour, 5 minutes. For the deployment I mentioned in the lecture theater of our department building, these sensors were sending messages every 1 minute because we wanted to have kind of an advanced deployment to see how quick the CO2 actually tended to rise. And if we had set our update period to 5 minutes, we wouldn't have had the same granularity that ended up being essential. So maybe for future deployments where you don't really need that much of data being collected, you could probably get away with 5 minutes. So for example, for 1 minute update period with best network strength, these sensors are going to last 2 years, I believe, 1.5 years to 2 years. If you set it to send updates every 5 minutes, let's say, these sensors can last up to 5-7 years. So it's quite a long time, so you wouldn't have to worry about it. And the price, I believe the pricing per unit is, it varies from different vendors. But if you're buying them in bulk, obviously it can get a lot cheaper. And I believe we got the price possibly down to like 50 euros or 50 pounds per unit.
Okay, good. And considering this is a work in progress that you described, what next steps do you envision?
I have to describe the small paragraph we wanted to discuss. So there were several strands or several directions we wanted to look into. So first of all was the complex event recognition. So having many different sources of data coming in at the same time, how do we combine different readings to see what's been happening in the building or in a specific room? So just by rising CO2 levels, you can see that someone's probably in the building or in a specific room, right? But then what else can you infer? And this is a especially important research topic when you combine CO2 sensors, for example, something like smart plugs, where you can see that some of the devices are being powered like monitors, right? And they consume more electricity. And then that gives you different levels for analysis. Another part is privacy. So if you have a system like that, you probably don't want to deploy it in a building immediately, because again, if you can see that someone's in the office, you might want to have people a choice to be able to opt out of it and not being able to, just look on everyone. So we're writing a privacy engine that only allows specific users to look at their immediate surroundings and possibly only their office rather than the entire building at once. And then other things include building automation, and then again we have feedback loops with sensors and actuators in the same building. That leads to the final aspect, which is kind of formal verification and interoperability with the available standards that most of the people here seem to be working on, which is very exciting.
Okay, good. Thank you. I believe we have another question for Vivian. About the operational analysis, whether you used any standardized methods on operational rating, and actually, have you concluded in any results for the score? How?
Yes.
I can give some background on the question if I'm allowed, Panayoda.
Yes, Paris, of course.
This is a topic that we are also facing in the EPC, the fact that we do not have a joint understanding in terms of standards for many aspects of operational rating. Okay, of course, in your case, you are discussing about comfort operational assessment. And I've seen these 60 pages that you have attached. You rely mainly on some standards like the 77300 for the ergonomics, or the 16798, or for lighting the 15,900 something. So I've seen the standards that we are using there. What I would just like to mention is that I wanted to know if there are any other operational standards or standards for operational rating that you might have used for developing this method. And just to mention in brief, and that's all that I have to say, that we are trying to initiate at this point a working group under the SEN for operational rating, developing and delivering some indicators which would be commonly accepted on that field. So it might be interesting to discuss this with you as well, if you would like to be part of that. So my question is fully understood and replied by you, but of
Perfect.
course.
Yeah. Thank you, Paris, for this. Yes, as I also mentioned in the chat, so everything that we done was based on the standards. So we really followed the standards, and we were also based on the other frameworks, as I mentioned, that the levels or some detail index that was developed by the Aldrin project. So within the guideline, you can see all the details about the monitoring, because it was based on EU standards and following, how can I say, correct steps. They didn't come out of our head. However, if you would like, we could even have like a bilateral call at a separate call, so we can discuss in detail and give you some ideas. And as I also say, also here in the team that we are working, and this is also, and I guess that this should also be the scope of this of the call, that we are coming, different people from different projects, that we should not be aiming to create something new every time in every Horizon project. This should not be the aim, because we create something new and then it stays in a drawer, it's published on the relevant side of the Commission. This should not be the aim. If we find something that is good, we should take this tool that it was developed from a project and then build on that one and try to adjust that into the other needs. There should not be constantly something new, because the issue with that is that we end up having too many tools. No one knows which tool to use, and then the tool loses the reliability. So me being involved in these two different projects, what I will try to do, for example, take the Extendo as a basis and then build upon that one and adjust it to the needs for the IBRO to EPC. So I think that this should be a general message, so for everyone. But of course, I'm happy for another call. If you want, we can tell you details, and you can also use this tool. We can also explain to you what we did in detail, and you can take ideas on and base your work on that work.
we fully agree on that, and that is why in D2EPC we mainly rely on existing standards. So we fully agree that we see many new methodologies being created by many new projects.
Yeah.
Just staying in Sandros. So this is what we said as well. We don't want to create a new methodology which will be just lost after the completion of the project.
Exactly.
Let's rely on standards. Let's rely on commonly accepted methodologies.
Exactly. We'll be more than happy if you decide to move on with the extended approach, and we'll be more than happy to also support you and see how we can help you with that.
Thank you, Vivian. This is something that for sure we will consider. Thank you. Thanos Kalamaris also has raised his hand. Thanos, do you have a question?
Yes, I would like, since as I observed from Vivian's presentation, that pretty much we measure the same things, at least a subset, the temperature, the humidity, and the CO2. I would like to see a more sophisticated approach on their incorporated indicators. How you deliver the score of thermal comfort in the final to the end user, to inform the user. If I believe it was next to the last slide, you delivered some percentages in regards with thermal, air quality, visual comfort, and acoustic. I would like to see the methodology, if it's available publicly, how you end up in this, how you utilize these measurements, these metrics, and you end up in this assessment for the thermal, visual, and air quality. If it's
yeah, sure, definitely. I don't know about the time we have, but I could happily go through the spreadsheet that we developed. I mean, in this presentation, I didn't want to get into a lot of technical details.
Mine was technical.
Yeah. No, I understand. I avoided showing this intellectual spreadsheets with that just as presented. Also, you presented. I tried to make, but so that you know, I can just briefly show you how the spreadsheet looks like, and. Can you see my screen?
Yes.
Okay, so you can see my screen now. So starting, for example, from the comfort rating, this is the result. This is the thermal comfort, and this is where we start. From example, copy-pasting the information that we get from the measurements: temperature, relative humidity, CO2. And then from this one, we get the, based on the weighting we decide, we come up with a scoring for each of these different parameters. So we have these measurements here, we have the survey here. That answer is answered from the question is from a predefined list of answers.
Okay. So you correlate the measurements.
And then,
sorry. You may.
Yeah. So I mean, it's much more complicated than a single index. So it comes from detailed analysis also for the air quality. We have the calculations. We've taken a lot of things into account, and we have defined these 4 categories based on the standards. We have the surveys, we have the checklist, and then the visual comfort. We have again the measurements. So it's much more of a complex thing coming behind this one. Of course, as I said, we're more than happy to say more than that, even though the aim of this presentation was mostly to present the hybrid of EPC, but also talking about extended, because we're aiming to get some of the things developed in the extended to bring them here. But happy to spread the word for the work we did in extended, because it's a really good work and it's based on very deep analysis that we did. So we would be more than happy if you would use the tool, and we can happily explain to you the spreadsheets and how it works.
Just to see your approach.
Yeah.
I guess you correlated comfort with the occupants' feedback. So you correlate measurements with feedback, as I might understand with this sneak peek that I had on your tools.
We did that as well. However, this was not the aim of this one here, of this project, because now everything has to do with the EPCs. So how we can integrate that in the EPCs. So I mean, the comparison between the measurements and the actual and the perception of the occupants is not really the aim here, because here is to get the a general evaluation of the indoor environment based on either the one or the other one, and just get like a scoring, but not to get like a, like say, more researchy approach on how good our measurements are if they're approaching, because also the perception is something very personal. Yes, so how if I'm Greek, so I'm more cold than everyone here. So being in Brussels, I'm always complaining that I'm cold, whereas the others are not. So the perception is a bit something more personal.
I totally agree with you.
Yeah. So. Happy to discuss more with you. Thank you.
Thank you very, very much for your feedback.
Thank you, Thanos.
I think there is also a last raised hand. Maybe we can move on to next question from Kumar. Yeah. Do you have a question?
Yeah, I have a general statement. So I have been exploring lots of EPC databases across member states, and I have been following Extendo's work. Like, you guys are doing a remarkable job, and the tool seems to be really promising. So, like, I will love to talk to you regarding the data quality of the EPC database, like on one-to-one. This is for Vivian.
Can you please repeat, Kumar? I guess you also know Zuhaib, since if you're involved with it. Can you please repeat? Can you please repeat the question?
Yeah. So this is not a question. Like, I am giving a general statement. I have been following Extendo project, and I love whatever you guys are doing, especially in terms of maintaining data quality of EPC database. And I myself is dealing with EPC database here in Ireland. So in next session, I will be presenting those findings, but I would love to contact you one-to-one if I have any questions.
Sure, Kumar. Yeah. Sure, Kumar. And so that you know that this is also the aim of the Able to EPC, to maintain this quality and reliability of the results, and also make EPCs more and user-friendly, and of course more attractive to the building owners as well, and have this building renovation passport and give value to the logbooks.
Yeah, so Ireland is not the partner in that project Extendo, but we have similar kind of methodology and similar issues.
Maybe you can continue the discussion. So I believe this concludes any questions for the session. Thank you. Miriam, probably we can have a coffee break now.
Yes, so this was a really fruitful discussion, but now it's time for a short break. I think 15 minutes would be enough. So meeting 20 minutes past 12.
Great.
Okay? And then continue with session 3. Okay, I think more or less we are back. So it's time for our session 3, so advancements in building sustainability assessment. And just to remind you again, any questions you have, please write them in the chat, and we will discuss them at the end of each session. So we can start with our first presentation in this session. Daniel Leira from EDICE project from Aalborg University. You can start with your presentation.
Thank you. You are probably seeing my screen now?
Yes.
Okay, perfect then. Once again, my name is Daniel Leira. I'm from Aalborg University in Denmark, and I'm with Giacomo that also presented right in the beginning of this workshop in the EDICE project. My presentation is called the methodology to estimate space heating and domestic hot water energy demand in buildings from low resolution heat meter data. I know it's a big title, however, just cope with me and you will start to understand what do I mean with this. Small agenda of today. I will just show you my contact info if someone wants to reach me afterwards, the problem formulation and objectives of this methodology that we developed, the proper methodology of let's call it brick by brick or step by step that I will show to you, some results when we applied the developed method in some building cases, and then some conclusions, further work, and the current status of publications right now regarding what we have been working on. So again, Daniel Iria, I'm a PhD at Aalborg University. I'm related a lot in EDI's project. However, I'm also in a project that is a bit similar in some points called Prelude, and then my contact info. So problem formulation. We have, at least in Denmark and in a lot of European countries, we get energy, heating energy to throughout district heating network. And since a few years ago, these district heating companies have been installing energy smart meters to their customers. However, they are only installing one. And they are only measuring the total energy usage, mostly for billing. And this is not good for us researchers and also for them nowadays, when they really want to understand how much energy is being used to the buildings in terms of space heating, or if this energy is being used primarily to domestic hot water, so showers, cooking, and so on. Therefore, we, instead of just putting one more smart meter, since a few years ago, a lot of people have been developing methodologies to disaggregate in the data that we get from one smart meter, how much energy goes for spacing and how much goes to domestic hot water. Some problems have been raised so far, like, for example, some of these methods only work with 15 minutes, 10 minutes data, and usually, for example, these meters only measure hourly, but also some of the methods already developed, they need a lot of information about the buildings. They need all the thermal characteristics of the building, they need the occupancy, occupancy profile, and this is usually information that we don't get. Therefore, the objective is to try to disaggregate both space heating and domestic hot water from this data, however, using hourly measurements and also having the minimum information that we have. Therefore, only the meters data, but also weather data. And that was the main objective of our methodology. And that's what we have been working so far. So what we did and what you are seeing right now is let's call it an algorithm or a flow chart of how the methodology works. So as soon as we get the data, which is from the smart meters and the weather data, we pre-process this data, we clean it with some wrong values that might exist or some missing values that also might exist. We take care of that. And then the second stage is to understand, or let's call it, differentiate some of the points that are only for space heating, where are other points that is space heating and domestic hot water. Usually in Denmark, people, when they use space heating, they turn on and they leave it. They leave the heater working throughout the day. However, for domestic hot water, it doesn't happen like that. It's usually an episode. So, for example, in the morning, we usually get up and we take a shower. So during that morning period, there is domestic hot water being used. However, after the showering period, let's call it like this, people go to their jobs. Therefore, no domestic hot water is being used anymore, but only space heating. Therefore, the second step of our methodology is to differentiate or to detect where are the points where domestic hot water is being used or produced, and then what are the other points that is only space heating. So that was the second step. Then the third step was, okay, from the points that we detected where is domestic hot water, let's try to find in these points how much is the space heating only. And we developed some methods to make this calculation, and I will show you afterwards. And then in the end, on the step 4, on the validation, we used several building cases where we compared their measurements with our results. And we also compare with some domestic hot water compliances, which I will also explain a little bit further. But just again, regarding the separation of this data, trying to detect what are the period of time where domestic hot water is being used. We tried several ways. The best one was throughout maximum values. So we defined that would be only 7 points throughout 24 hours. So 24 data points of a day. 7 of these points will have domestic hot water, and the ones that will have domestic hot water are the maximum points throughout the profile. So as you can see, the red dots in this slide is the ones with domestic hot water, and then they are also the maximum of the profile. Then and then the green ones, it's only space seeding. Yeah. Then what we did is, I will go back, is that the red ones, they will be removed from our data set. And when I say removed, it's not really removed, completely eliminated, but we'll make them disappear somehow. And what we are going to do is trying to estimate them only based on the green points. And by doing that, what is going to happen is that the red points will be estimated only their space seeding, because when you calculate them, it's only based on the space seeding values. And for us to calculate afterwards the domestic hot water is that, okay, we estimated the red points space seeding based on the green points, and then the difference of the total measurement with the estimated space seeding will be our domestic hot water. That's how we do it. And one of the big problems that we got from this is that sometimes we might have 3-4 hours of red points, let's call it like this. Therefore, when we have big gaps, we cannot just estimate the space seeding throughout a smoothing techniques that we used. Therefore, when we have higher intervals or gaps of 2 hours of red points, we used another methodology to estimate the space seeding, which will be the SVR, or support vector regressor. Therefore, for intervals of 2 hours or less, we are just going to use a smoothing technique to estimate the space seeding. And then when we have higher hours of gap, like 3, 4, 5 points in a row, then we use a SVR. And the main difference is that the smoothing is that the smoothing, it's only based on the smart meters data, and so the total measurements, and the SVR, it's not just based on the energy, but also it takes into consideration the global radiation and the outdoor temperature to estimate the space seeding. In terms of results, we used 28 apartments in Denmark, also a full apartment block in Switzerland. So it means that we had several single family houses connected, and then we just summed up, and we have a smart meter only for all of the that is measuring the energy to all these houses. We also used the theater in Italy and also a rehabilitation center in Italy. And then we also compare with the domestic hot water compliances of different countries. So for example, in Denmark, to estimate the domestic hot water, they usually consider only the area, or the heated area of the house. However, for example, in Switzerland, they also use the number of people besides the area. And also in Italy, it was a bit different because we tried to evaluate the theater and rehabilitation institution, which is a different apartment compared with residential. Therefore, there was some other conditions that they have in their formulation to estimate the domestic hot water. So what we did is that we estimated domestic hot water throughout the compliances, and then we compare with our methodology to see which one is estimating more accurately the domestic hot water. And this was the results. So when we use decimal data, therefore our smart meter is measuring the total heat with decimal values. We have a great accuracy in terms of the estimated comparing with the measurements. In red points or red squares is when our on the right side is our estimations, and then on the left side, also some percentages, is with the error between the measurements and the compliances. And if it's in red, it means that that one performed better than the other. So as you can see, the table that is most red is our methodology comparing with the one from the domestic hot water compliances. So it means that we are estimating more accurately the domestic hot water than the compliances. The methodology performed even better for estimating the space heating, as you can see on the graph right on the right as well. But there was a big problem, and that's something that we are currently trying to solve, is that when we don't have decimal data, but rounded data, this means instead of having 1.123 kilowatt hour of energy, our smart meter is only measuring 1 kilowatt or 2 kilowatts, 3, 4, and so on kilowatts without any decimals. And that it's a big problem that we are trying to solve, because as you can see, the same table, however, with with the same building cases. However, as soon as we start to use rounded data over decimal data, then the method stops to work correctly. The error between the measurements and the estimation, it becomes really big. And therefore, the compliances estimation that I showed you before, it starts to, of course, perform better because it continues the same values, the same percentage as the other table. However, on this one, just because by using rounded values, the estimation methodology that we develop is not working that correct. And we are working right now to solve it. However, that's one of the conclusions, and it's something that we are trying to talk with the district heating companies, is that they should try to have meters that measured with decimals. Also, not just because of our method's sake, but also other methodologies and other companies that are working with them, they are saying exactly the same thing. Having rounded data doesn't work because of several reasons, and one of them, as we can see, it's on this methodology. So in terms of further work, is that we are trying to improve this methodology for the rounded measurements and also commercial cases, as we had before I showed you. We also want to applying this methodology to other data sets from other countries, and also with other heating appliances, because some heating appliances might have, like, for example, a storage tank for domestic hot water. Others, it's as a lot in Denmark, we only have a heat exchanger. I know that, for example, from my country of origin, we use small boilers for it. Therefore, different systems will probably have different results. And also, we are trying to benchmark this methodology with other existing methodologies, and we are trying to compare them with the common data set. And also, we always advise that we should collect more good quality data to work more on these methodologies, because we believe that data is the future. And last but not least, some of the publications that we have been working on and published, and two in bold are the ones respecting this methodology, where one of them is right now under review and the other is for a conference which was accepted to be in this August. Thank you for your attention.
Thank you very much, Daniel. Very interesting presentation. And moving on to the next one from Kumar Rauskhan, PhD researcher at TU Dublin. So yeah, we're ready for your presentation.
Yeah, thank you for introduction. Let me share my screen. Can you see my screen?
Yes.
Yeah. So thank you very much for inviting me to present my work in this workshop. And I'm Kumar Roshan, a PhD student at TU Dublin, and my research project is making building stock energy analysis robust. So a bit of background here. Buildings are single largest energy consumers in Europe, and residential alone is responsible for quarter of the all CO2 emission. So back in 2010, EPVT mandated EPCs to be issued whenever a building is constructed, sold, leased. And in return, member states were supposed to accurately inform on their reference dwellings in a common, transparent manner to facilitate calculation of cost-optimal retrofit interventions that will avoid the lock-in period. So this whole exercise resulted in member states amassing lots of thermophysical data on their building stock. And it also resulted in member state creating large national databases on EPC. Coming down to Irish EPC database, it contains more than 1 million EPC entries, and it is representative of 50% of the whole dwelling stock. And since 2014, it is available in the public domain. And here in Ireland, we use deep methodology to produce EPC, which factors in more than 200 variables and needs a site visit to complete the assessment. And this and the whole EPC database is available in public domain since 2014, and the database is statistically significantly disaggregated, and data is really suitable for bottom-up stock model. So to understand why the reliability of EPC database matters. So because it was by design an asset rating, but its use goes beyond just being asset rating, and currently it is being used to support research, even to calculate bank mortgages rate. So it is also being used to derive energy policies by government and to track down the rate and effectiveness of the renovation. So in Ireland, is projecting to retrofit 500,000 homes by 2030 to B2 rating at a cost of 8 billion. So therefore, an unreliable EPC database could have financial consequences. So before proceeding further, we wanted to understand the data. We ran analysis and found out that 1/3 of the database is based on unrealistic thermal default values. And here in the first chart, it could be noticed like if you use empirical data instead of default, then there will be energy performance gap. And this energy performance gap is more pronounced in pre-thermal era dwellings. And in second chart, it is a typical frequency distribution of Irish dwelling for walls and roof U values. And by nature, this chart is bimodal. And there is reason behind that. Mode 1 represents new construction or the dwellings which have been retrofitted. And then we have more spread out distribution for mode 2, which is as built or existing dwelling. And there is one anomalous spike here, and that represents default values. And I will later on explain what that is. So before moving forward, we wanted to understand how default is being used in different member states. And then we found out there are two ways and two categories of handling those default values. One is dedicated to unknown construction, and then other is for broadly known construction. And every member state, they have different set of default options available. In France, we have 48 options available to document unknown wall types, and in Ireland we have only 11. And then for broadly known, UK does not support unknown construction to be documented. So they have 348 options available to document unknown, broadly known wall types. And here in Ireland, we have 110. Furthermore, we wanted to understand the source of all these default values. So we looked into deep methodology and found this table, which is the source of default values for walls. And we further stripped it down and then found some sort of pattern here and the explanation why we are seeing that anomalous spike in the U value distribution. So if we look closer, although it is supposed to be 121 options, but we have only these many default options available to produce EPC. And this default value relates to wall. And here you could see we have unknown highlighted in red, and in blue we have this single leaf uninsulated construction. So both have 2.1 U value. And the reason behind it is assumed that whatever dwelling predates to the thermal regulation are uninsulated and hence being provided with real bad U value. And if we look at the post-thermal U values, then it is surprising to see, but irrespective of wall type, we have only singular U values available. So it doesn't even matter like what wall type assessor will select. The default U value will remain the same. So again, it is not motivating the EPC assessor to go beyond and look for more details. Furthermore, we wanted to see how much unknown we are dealing with in the EPC database. And then this chart shows the distribution of different wall type, and surprising to see unknown is the third largest chunk of the database at 16%, which is statistically significant and needs to be looked into. Furthermore, we wanted to understand what is the distribution of those unknown entries within across the construction period, and then we found out it is more pronounced in the post-thermal. Surprising to see, because there is a common understanding like unknown construction are only used when you are not able to access the details on construction of dwelling. So this debunks that assumption, and it is rampant and being used for the newer construction. And within post-thermal, we found out 40% of all entries are based on unknown wall types. So the question remains, is it so black and white? We could document the wall types using only 8 broadly known and 1 unknown wall types. I guess it's not. And then for that, we evaluated the evolution of wall types in Ireland, and we ended up documenting 21 wall types, which could possibly be available in the Irish dwelling. And in this chart, we documented every wall, and then in red, it shows the change in predominant wall types in the chart, and then shaded are the pre, post-thermal, and then housing boom period in the Ireland. This chart also documents major events which might have influenced the material change and change in construction method. Further, we use that chart to identify and establish the predominant wall type for each construction period here in Ireland. And then we went ahead and calculated the theoretical U values for all those walls. So, and this chart also represents the differences, and the maximum difference we found was 274% in case of concrete hollow block wall. So as an outcome of first leg of my research, we have developed a method and named it find and replace. So this table is created to find and replace unknown wall types and its associated U value in the EPC database to make it more representative. And here we have creative construction, predominant wall type, and its U value. So it will work something like that. If you see unknown wall type in the database, and if the default
if the value aligns with the default available here, then go to the construction period based on year of construction of that dwelling, pick the right predominant wall type and replace it with a more representative U value. Similarly, we also created the method to update U values related to broadly known construction, and this will work slightly differently. So here we know the wall type, but the U values, those are not representative. So in this case, we will be preserving the wall type labels and only replacing the U value. For example, if the wall description is stone and it was constructed pre-1900, and if a U value of 2.1 is associated, then replace it with 2.69, which is more representative. And we have, like I have presented the case of wall, but we have repeated this process for other building fabric element, for example, floors, roofs, and windows. And currently we are in a process of developing these filters because we know EPC database is not perfect and it is prone to human error. Although we have so many auditing process, but somehow the erroneous entry keeps on landing in the EPC database. So we are using our domain knowledge and data-driven approach to create these filters because not two variables are same. And we are looking into these three groups of features, dwelling geometry, thermophysical data, and the system efficiency data. For one example here, we have the distribution plot for floor area, and it is skewed. It is positively skewed, not normal. So we try to use different approaches. And here, for example, we used a box plot, but because this is positively skewed, so it was not working well. So we end up using the existing box plot, the process which have been developed by KU Leuven, and it factors in the data which are positively skewed or negatively skewed. So we found out this method works well with these kind of distribution. And similarly, we will be going through different features which does influence the energy performance of the dwelling and try to custom made filters for all those. And so what is the impact of all these findings? So the method we have developed will mitigate the discrepancy happening because of unrealistic default value use. And the method we have developed, if used, will reduce the thermal energy performance gap, and it will improve the credibility and reliability of the EPC database. And we are also planning to script it in Python and make it available to common forum. So it could be used by other people, whoever wants to use EPC database to extract information or create a stock model. And we are currently in process of submitting the findings in journal. So what is the future steps? So the 80% of all data science project is cleaning database, preparing it, and then utilizing it. So we are in process of pre-processing data, and it will be followed by use of cluster analysis, and we are hoping to use unsupervised machine learning instead of using arbitrary choices to define reference dwelling. And we are hoping to get unconventional reference dwellings, which are really representative and which gives insight into dwelling stock to create custom-made retrofitting plans. So at end, I will be automating all these processes. So the whole EPC database is dynamic in nature, and to deal with that, we need dynamic tools. And it will keep on, the script will keep on adapting with the database and keep on changing the limits to filtering of data based on whatever distribution is there. And I will be ending up by aggregating all those reference dwelling to create a robust dwelling stock model. That's all I have for now. I will be glad to answer any questions. you might have.
Thank you very much, Kumar. We are already collecting questions in the chat.
Yeah.
But first, we continue with our last presentation in session 3. And again, finishing the session with a presentation from the D2EPC project from Paris Kaides from Frederick University. Paris, you can start with your presentation.
Okay, thank you, Mia. And once more, very excited and very happy to host all the friends from sister projects and from other relevant activities. We hope that D2EPC will contribute to the enrichment of the information provided to the users of EPCs, and that it will also has its minor contribution to the improvement of the classification scheme. Now, what I will present today is related to the integration of LCA indicators into the energy performance certificate. This is certificates. This is one of the major aspects that we envision to implement in the D2EPC project. And I will just show the D2EPC approach, discussing about some aspects that we have managed to achieve the past few months while the project is being implemented, and also giving you our aspect and our views how we envision that to be realized in the future. Now, the basis of our approach is that the sustainability assessment is an integral aspect of the energy assessment of buildings. We have developed several indicators which integrate the effort, the resources required to deliver building materials and in general the building shell with aspects related to the energy performance of the building. We have reached, let's say, the maturity as scientific community to deliver indicators such as the energy payback period of a building, discussing of the embodied energy in a building over the saved energy, for example, of a building due to improved energy performance. So having achieved all that, and also having delivered numerous methodologies which are used for assessing the life cycle assessment of buildings, the vision and what the D2EPC aspires to do is that we aspire to integrate this set of environmental indicators in the information provided to the user in the environmental performance certificates. And actually what we will present in this session is our approach, how we envision the integration of LCA indicators into EPCs. Another important aspect about D2EPC before we proceed is that D2EPC is a BIM-oriented approach. So we do recognize the fact that the digitization of the assessment of the built environment has introduced BIM as the main, let's say, reference for collecting all information related to buildings, and that is why our approach in all the tasks that are related to the enriched indicators for buildings, including LCA, are based on the fact that we anticipate to get the information that we need to develop the indicators that we wish to include in the next generation EPCs from BIM literacy, from BIM files. So having said that, the D2EPC approach on that was, of course, first to define the LCA indicators which would be used for the purpose of enriching the EPC with this information, the sustainability information. And of course, in order to do that, we started with an overview of the existing methodologies of LCA. This, though, was a very easy task for the reason that when we were drafting the proposal back in 2019, levels scheme was still not, let's say, officially announced or established. When we started with the implementation of the project, we realized that as European research community, we have a tool, which is levels, which is used brightly in the field of sustainability assessment, which it should also be used in our case, and we will demonstrate in the following slides how we adopted this approach. Also, what needs to be discussed and what we analyze and what we are still analyzing in terms of D2EPC is information that we can retrieve from BIM files in order to conduct the LCA assessment of buildings. And at this point, this was a common result, a common conclusion from all tasks related to D2EPC indicators. The fact that at this point, the BIM files, they do concern a lot of information for the built-in shell, but in many occasions, information for built-in systems is limited. To this end, our approach from the onset, at least for the LCA, was to put some boundaries related to the built-in shell, not to the built-in systems. Therefore, our approach and what we will present later is mainly related to the sustainability assessment of building materials, building elements, and not of building systems. And of course, we envision in the future to reach that degree of maturity in our digital files in BIM, have all the attributes and the common language, solving all interoperability issues, so that we are also able to do the assessment of the built-in systems in terms of LCA. And of course, we are able, as I said, to deliver specific indicators, which were finally based on the levels scheme. And at the same time, under this, let's say, exercise, we also delivered some energy indicators, which were based on the life cycle approach, and which were merely operational indicators. At this point, it is important to state that the LCA indicators are asset indicators. That is, they are not affected by the actual operation of the building. They are mainly LCA indicators, that is, they are based on the construction of the building, whereas the analysis that we did for the operational indicators, it was more based on the actual operation of the building. But these are energy indicators, not LCA indicators, which we will present in this presentation. And of course, as we already mentioned, we were able under this exercise to identify the gaps in BIM documentation, which need to be improved in the future towards receiving more information for assessing the actual energy performance of buildings. Now, this, what you see here is a well-established schema in the field of sustainability assessment of buildings, the approach of the EN 15978 standard. As we said earlier, and we discussed with VPIE, and we agree on the fact that it's not the mission of every project to deliver a new methodology which will just stay in some drawers and will be forgotten a few years after the implementation of the project. It's our mission to develop our methodologies, our approaches based on standards, based on our common understanding on technical aspects of building. So to this end, our approach was also based on the well-established standards, on the 15978 standard, as well as on the 15643 series standards. And this was our, let's say, the stepping stone where we started assessing the indicators that would be used for this purpose. Of course, we did our exercise with the JRC data sets related to different methodologies for LCA. But as I said, this was at the initial stages of the project. Whereas at this point, we have finalized our decision to rely on levels. Now, levels is a European approach for assessing the sustainability of buildings, which was adopted now 2-3 years, is mainly established in our regions. And in order to choose and proceed with specific indicators to integrate, we have based our work on the levels indicators, which are those that you can see in this slide. So, of course, indicators which are related to climate change, to ozone depletion, to acidification potential, and so forth. Well-established indicators which are used in the case of LCA. And of course, the other important aspect about our approach is that we rely on specific boundaries. That is, we do not assess the operational stage of the building. We only assess the construction stage of the building. And we do feel, having said that we rely on standards, we do feel that all these assumptions that are performed for the operational performance of buildings towards delivering a cradle to grave analysis may not be that, let's say, precise for the case of buildings. So our strategic decision was to limit our boundaries for the LCA indicators from cradle to gate, that is, from the extraction of the resources for extracting, for delivering, for manufacturing the building materials until the construction of the building. So these are the boundaries that we are using towards reaching more consistent results in the assessment of buildings, because we always need to have in mind that EPC is about classification, it's about comparing buildings. It's not about absolute assessment of buildings. It's not, let's say, it is a calculation tool, but it is actually a classification tool. We want to compare buildings. So in order to have a common basis for comparison, we restrict our limits to the level of the gate, that is to the level of delivery of the construction. And of course, we have followed the different steps in accordance to 15978, and of course in accordance to levels to deliver the indicators that are going to be used for for enriching information for sustainability in EPCs. These indicators, these stages are actually provided in the slide. The construction of materials, transportation to site, the construction and installation process, the energy use, the water use, and as I said, the deconstruction is not within the boundaries that we analyze. Now, in order to demonstrate the concept towards developing the required tools for adapting this practice in the EPCs, we conducted a case study in which we used a pilot of D3PC, that is the Frederick University New Wing. It's one of the 5 pilots of the project. We did the analysis of the building materials with the use of an IFC parser. We were able to extract information from the bin file of all building materials. And by combining the bills of quantities with the EPDs of these materials, that is environmental product declaration of these materials, we were able to deliver, to develop and deliver the indicators, the LCA indicators that we propose and we envision to include as well in the classification scheme. Some information about our pilot: it's a mixed use building found located in Nicosia. You can find more information on the building, for the building, in our webpage of the D3PC project. And these are some indicative indicators that were extracted for some of the stages, the life stages of the project. And apparently this information is not a simple information. It cannot be perceived simply by the user, but our idea for D3PC is that we will give the option to the user to choose which, let's say, indicators and at which stage would wish to be presented and of course classified. Now, as I said, another aspect of our work was related to the extraction of energy indicators, operational energy indicators. For that, we have proceeded with a combination of different, let's say, aspects in the ratio of defining the energy assessment of buildings. This is the set of indicators that we have developed. Now, this exercise is actually not strictly related to the life cycle assessment, but it was under the task that we are implementing for D3PC, and we found it useful to demonstrate this set of indicators. This was also the discussion that we had earlier for the presentation of DPIE, stating that at this point we do not have, let's say, a commonly accepted set of operational indicators for classification of buildings. In D3PC, we have introduced a rationale stating what we will consider in both ratios of the energy assessment, and we have delivered a set of indicators which we are going to use towards assessing the actual energy performance of buildings. With that, I would like to complete what concerns the energy performance in LCA indicators, and I would be happy to answer any question that you may have. Thank you.
Thank you, Paris, for your presentation. And with this one, we have concluded session 3. So now it's time for questions and discussions.
Yes, thank you, Mia. Well, we have some questions for the first presenter, for Daniel. Well, those are the domestic hot water companies are interested in changing their approach from round numbers to decimals. So you can elaborate more on that and have also in mind what is the reason behind having rounded data, if this has to do with the power provider's policy, or if it can influence changes to charges, to the consumer.
Regarding the rounded data, it's not a policy from the district heating providers. It's from the companies itself of the smart meters. So, for example, in Denmark, what we use right now, it's a big meters provider. It's called Kamstrup. Probably some of you know this company, and they are the ones responsible for this data. The district heating companies that we are working on with, they are really interested also to have this decimal data, and they are actually the ones that have the weight to change this in the companies that are providing these meters, because they are big companies that buy probably thousands and thousands of these meters. If it's only us as a university, if we ask them to do it, we don't have, I don't think, that much influence over them. However, these big companies have. And that's what we are talking to them, and they are becoming more and more aware of this issue, and that's something that they are talking right now with the meter providers. And I know that right after there was a question from Alexander, and yes,
I think I've included them both. I don't know if there is another one from Alexander, but so that means that after the you don't have access to the decimal numbers in the meter, right? They're not rounded after. You just receive rounded numbers.
We receive them rounded. However, we know by the fact that the meters is measuring it with decimals.
Okay, so there is access if someone wishes to check the decimal numbers.
Yes, but what we are working on, it's with 1 year data, which is hourly. So, and we have like thousands of buildings. So therefore, what we know for a fact that if we go to the meter, we'll see the decimals. However, we do not receive them. So it's as far as I know, it's a little bit more of software implications, that it's the meter providers that should work on this. But as far as I know, they right now, the district heating companies, they are having some talks with them to see if it's possible to change this policy. Because also one thing that we have seen, it's a small shift, which is before the data was just for billing. So they just wanted the total value to see how much they would charge the customers. But right now we are using the data more for understanding our building stock and how and make ways of assessing it, and to afterwards optimizing it or improve it. So it's not billing anymore, and that's why the decimals, it's so necessary.
Okay, thank you, Daniel. There are some questions also for Kumar about the find and replace method. Is this done automatically or should be done manually? You can elaborate more on your answer in the chat, maybe.
Can you hear me?
Yeah, yes. No.
Yeah. So in general, that work is done manually, and it's kind of prerequisite you will do that processing before using that EPC database. So what I'm planning to do is to script that whatever I have found and script it in Python. So whenever you need to replace those values, you just use that script and it will do it for you, the whole find and replace.
Okay, and another question is whether there is some feedback loop along the system to improve its understanding of the stock as more buildings are processed.
Yeah, so as we know, like it's ever evolving, and the values keeps on changing. Once a dwelling gets a new EPC, the old one gets deleted and the new one is entered in the national EPC database. So it's dynamic in nature, the whole database, and it keeps on updating fortnightly. So the idea is to have this data-driven approach, develop functions which will factor in ever-changing data, if you recall my chart, like by modal chart, so we have this new construction which are there in the mode 1, and then we have more distributed mode 2. But in future, all mode 2 dwellings will transfer into mode 1 by means of getting upgraded and will have better U values. So it will factor in those kind of changes.
Okay, thank you. I don't see any more questions in the chat or raised hand. So probably we can proceed with the last session of our workshop. I'm not sure if actually we are having some trouble with the first presenter of the session, if I understand correctly, Mia?
Yes, that's correct. So the next session is session 4, monetizing buildings' energy performance, the use of life cycle costing indicators. The first presenter is Gerfried Sabrat, but I'm not sure he's here at this moment. So I suggest we continue with the second presentation and hope that he will join soon after.
Yes, that's okay.
Yeah, okay. So the second presentation in this session, I'm the presenter, so I will share my screen. Okay, so you should be able to see my screen now.
Yes.
So the title of this presentation is Analysis of Cost Economic Indicators for EPCs. I'm from DIMA Consultants in the Netherlands, and we are partner at the D2EPC project. So first I will start with the D2EPC objectives. So one of the objectives is the enhancement of EPCs through a novel set of indicators, aiming to simplify the understanding of buildings' energy performance and to present a more comprehensive overview of the actual energy performance of buildings. For that reason, within the D2EPC, we have defined a novel set of indicators, the smart readiness indicators, the human comfort and well-being indicators, the energy performance and LCA indicators, and financial indicators. So also kind of how we divided sessions of our workshop. And this presentation is focusing on the last one, so the financial indicators. So the objectives for the financial indicators are the establishment of simplified indicators, which will enhance the user-friendliness of the building certificate. Then the development of set of financial indicators based on the well-established concept of whole life cycle costing. Then the interpretation of the individual elements of building energy performance as a monetary normalized values. And finally, we wanted to enable the deployment of EPCs for the financial assessment of buildings' energy upgrade measures. So our all-in-all approach was divided into 3 steps. We started first with the literature review, then we continued to the methodology, where we defined the financial KPIs. We looked how we can integrate them into the D2EPC framework architecture, and we did the calculation of the financial indicators. In the last step, the third one, we developed the guidelines for the D2EPC integration. And here we looked at the real-life example of the Frederick building. We look at their measured data, and we did the example of the calculation. So if we look at the first one, so the literature review, here you can see the relevant standards that we reviewed. So starting with the Annex 56, then looking at the ISO standard for life cycle costing, then EN standard for sustainability of construction work and the calculation methods. We also looked at the previous deliverables within the project, where aspects of next generation EPCs definition, where EPCs were defined. And finally, we looked at the levels scheme. So this was just shortly about the literature review, and we can move on to the next step, which is methodology. So first, we wanted to define the financial KPIs. So the purpose of financial KPIs is to provide users with a real-time image of the monetized performance of the building. And the comparison between different scenarios will allow users to allocate the performance of the building. And so here the focus of the comparison is user behavior and his awareness of energy use, rather than the improvements of building system and envelope. So these financial indicators, they will not affect the energy class of the building, but the aim is that they will present an additional information to the user. So the overall idea is how to define the financial indicators is based on the comparison of the as operated energy consumption with the as designed energy consumption, with the as operated energy consumption but in the past time, with the predicted energy consumption, and with the building stock. Besides that, that comparison, the financial indicators also include the expected cost for the replacement and maintenance of building systems that will be explained later on. So after the definition, we had to look how to integrate this financial KPI into the D2EPC. So looking at the D2EPC framework architecture, we see there is a service and process layer, which includes a component calculation engine, which is a really important one because it is responsible for the calculations to assess the asset and operational performance through asset rating module and operational rating module. And besides that, we have the subcomponent building performance module, which is responsible for the overall calculation of the KPIs. So with this in mind, we can look at the inputs for the calculation. As it was mentioned in previous presentation, all these methods are BIM-based. So we have a digital twin, and the inputs that are required for this calculation, as mentioned before, come from the asset rating module and operational rating module. But besides, we will also need some information from the user. So with these inputs and with the building performance module that was mentioned before, we can calculate the financial KPIs as an output. So the inputs that we need, so the operational utility costs are described as costs for fuel for heating, cooling, power, lighting, water and sewage costs. But since water and sewage costs are not related to the energy use, they're excluded from this assessment. The required inputs were already mentioned before, but if we look a bit closer, what is required? So for the asset rating module, we need as designed energy consumption. For the operational rating module, we need as operated energy consumption. And from user, we need these things. So first, we need the price of the energy carrier. We would prefer to have this information from the user because this way we will have more accurate results, but there are also different tariff approaches in different countries. Then we would need the information about the energy carrier per energy use. We would also ask the user about the average expected inflation and discount rate. Again, this differs from country to country. And lastly, we would need building system information if that is not already retrieved from the BIM model. And with this, we would like to have information about the installation date and price of building system, their lifespan, and maintenance schedule and price. Then what we can calculate with that, first we did the as designed and as operated module. So what we did here is basically just multiplying the energy consumption with the energy price. And the outcomes of the as operated scenario includes cost in euro per month per energy use, cost in euro per month per energy carrier, and total costs in euro per month, per year, and per square meter. Similarly, we get outputs for the as designed model, where we can calculate the total cost in euro per month, per year, and per square meter. We can do the comparison between the two, where we can see the total cost in euro per month and per year, providing some additional information and thus increasing the user awareness regarding energy consumption. The as operated yearly cost in euro is a true reflection of the monetized energy use in the building, but it has to be mentioned that it does not really match the bills that the residents receive because additional costs like taxes are here omitted. After designed an as operated module, we also looked at the prediction model. So here we tried to evaluate the future costs based on the inflation rate and discount factor provided by the user. And we calculated the real cost, which is adjusted for inflation, the nominal cost, which has not been adjusted to inflation, and the net present value, which represents the future price in today's value that is determined with the discount rate. On the graph, you can see the comparison of all three, but this comparison is just an approximation, and it aims to illustrate to the user the impact of time on the value of money they will be paying for the energy use in their building. Then, as mentioned, we also looked at the building stock, but this can be considered as a future exploitation. What we want to do here is to present the monetized energy used on an expanded, larger scale and compare it with the building stock. So with some predefined criteria, the user could evaluate the performance of their building by comparing it to other similar buildings. Lastly was the expected cost for building systems. So here we summed up the expected cost for the maintenance and replacements of the system in the next few years. So the user can have like a timeline of the expected cost regarding building systems. In this table, you can see all the financial KPIs that have been defined. So as operated costs, as design costs, the comparison between the two, the predicted costs, and the expected costs for building systems. So this was the methodology, and we can move to the last part, which is development of guidelines for D2 EPC integration. Here we had a look at the demonstration case of Frederick University. It was also mentioned before by Paris. So it's a university building with lecture rooms and also a canteen at the ground floor. And it has 30 input meter data loggers, 45 input meter core data loggers, 3 zone monitoring and remote sensors for CO2, temperature, and relative humidity. And the measurement started in the middle of June last year. We had to do first several analyses in order to understand the measured data we are receiving from this demonstration case. First, we had to look at what kind of data we are receiving. Then we had to look at when this data started and how long has the measurement been going on, because this work was done in November. So at that point, we had some measurements, but for example, we could notice that some measurements haven't taken place yet. So we had to have an overview what is the time span of the measurements. And we also had to look at what kind of values we are receiving. So based on that, it was concluded that at that point, so in November, the currently available data was not sufficient for the initial calculation of the KPI. But nevertheless, the performed analysis of the available data was really beneficial because it provided us an overview of what kind of data can be retrieved from such installed meters. And based on the proposed methodology was adjusted to better fit the purpose. Nevertheless, we wanted to try the methodology. So we used different kind of numbers to do the example of the calculation of financial KPIs. You saw the results of the graphs in the previous slides. So this is how we then tested the methodology. So this was the last step of our approach. And if we sum up, our aim was to investigate the possibilities of integrating financial KPIs into the new generation EPCs, which will raise user awareness and provide additional information and thus improve the existing EPCs. The aim was also to make EPCs user-friendly. So with these financial KPIs, we allow the user to better understand their energy consumption because it is translated into monetary values, and such interpretation can be much clearer and more understandable, considering that tenants operate with money on a daily basis. So the outcome is that user can compare the monetary value of actual consumption with the monetary value of design consumption, can get an overview of predicted costs based on the inflation and discount rate, and get an estimation of future costs related to building systems. To conclude, the currently available EPCs, they already include some information about the monetary value of energy consumption, but they are based on design values, usually the yearly values, and the number of people usually needs to be considered as an average, and it does not include the energy use of household appliances. On the other hand, the financial KPIs within the D2EPC project, they use monetized values of energy consumption based on the monitor, so the operational use. So we get the insight into the monthly values, and it does reflect the actual consumption, so including the household appliances, and then there is no need to estimate the number of people in the building. Additionally, it also provides information about the predicted and estimated future values. And that would be all from my side.
Thank you, Mia, for the presentation. I don't think that Gerfried, our last presenter, actually joined at this point. So there is also a question for you in the chat. So maybe we can check this promptly. Do you think that this comparison may reduce the rebound effect by the Gibbons paradox by providing a target energy consumption and cost? It was done by Chris Murphy. If you need any clarifications.
Yeah, I would need a clarification to explain a bit more about the rebound effects. That would be easier then.
Oh, okay. Hi, good morning.
Hi. Good morning.
It is a well-known effect that when people have more efficient systems, that they think, oh, this won't consume much, so they stop, they relax. So for example, you buy an electric car instead of a fuel car, and people say, oh, this is cheap to run, so they do more mileage on the cars. And this sort of this rebound effect has been well documented, and it's also called the Gibbons paradox. So my question is, if you know that you live in a house with a very energy performant an energy performant house, that you think like, oh, I can use as much energy as I want because it's going to be cheap anyway, or it's going to, and by providing a target the way you do, saying, well, you shouldn't really, if you operate it well, you shouldn't be consuming more than this and it shouldn't be costing more than that, you keep that sort of tension so that people don't relax too much. It's just an idea.
Yeah, so it's a good point. Yeah, when we have something efficient, then we think we can use more. But the main point that's well, for the D2EPC and especially for these financial indicators is to raise user awareness. So they get the information, how much they're using, and they get this information in a really simple way. So exactly how much they are paying, which is easy to understand. And then, well, they can do with this information whatever they can, but the purpose is that it will trigger their mindset in a way that they know that they're using that much, but they could be using less or more depending on their behavior. So yeah, it can happen that then they see, well, I'm not paying that much, so actually I can be I can heat up the space, so that's of course the possibility. But as mentioned, the main purpose here is to increase awareness. So if they wish to do something about it, it's up to them, but they will have the information how much they are using.
And also, if I'm allowed to comment on that as well, hi Chris. We also have some tools, some AI tools in the project that are going to provide some recommendation and some benchmarking on different values and aspects on the building and its use. So probably they will have this information on how their actual performance would affect their behavior, how it would affect the performance of the building. So they would receive alert and notification in case this affects somehow the EPC grade, for example, or their consumption in that sense.
Okay, yeah, thank you very much. Sounds very interesting.
You're welcome. There are no other questions so far. If anyone wants to comment or jump into something, I believe that I really enjoyed this this workshop, and it actually triggered a lot of discussions, and we've seen very interesting presentations from all presenters. So thank you for your participation.
And I believe Gerfried is also not here to give us the last presentation.
Oh, well, something to look up for next time then.
Yeah, exactly.
So
Okay.
then we can conclude the workshop.
Yeah, we have come to an end. Thank you very much to all the presenters. It was really interesting to listen to your work, and I think everybody learned something new. Some new connections were formed, so it's really great. And we hope we can meet again in some other workshops, some other collaborations. And until then, I wish you a really good day, and thank you again for joining this workshop.
Thank you so much.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you. Bye.